What if the birth of the universe wasn't the cataclysmic explosion we've all imagined, but something far more mysterious, something silent, almost imperceptible, yet still echoing through the cosmos today? We often picture the Big Bang as a thunderous roar, a violent beginning to everything we know. But what if instead it was a moment of profound quiet, a rapid unfurling of space-time so subtle that its signature has been hiding in plain sight, waiting for us to learn how to listen? This isn't just science fiction. It's a revolutionary idea gaining traction among cosmologists, one that suggests the universe didn't begin with a bang, but with a whisper whose faint vibrations might still be shaping reality as we speak. In this video, we're setting out on a journey to explore one of the most captivating mysteries of modern science, the possibility that unheard frequencies, remnants of the Big Bang, are woven into the fabric of everything around us. These aren't sounds in the way we normally think of them. They're gravitational waves, quantum fluctuations, primordial signals, frequencies so far beyond human perception that they've remained hidden for nearly 14 billion years. Yet, they may hold the key to understanding why galaxies form the way they do, why matter clumps together into stars and planets, and perhaps even why life itself emerged in this particular universe. We'll dive into groundbreaking theories from visionaries like Alan Guth and Andre Linde, explore how instruments like LIGO are tuning into the faint ripples in spacetime, and question what it means if the universe is, at its heart, vibrational, a cosmic symphony playing in a register we're only beginning to hear. From the origins of everything to the hidden forces that might influence your everyday reality, we're uncovering secrets that challenge not only how we see the cosmos, but how we see ourselves within it. So settle in, open your mind, and get ready to explore the echoes of a silent beginning and just maybe discover that the universe has been speaking to us all along in a language we're finally learning to understand. Forget everything you think you know about the beginning of the universe for just a moment. That iconic, fiery explosion, the one depicted in countless documentaries and animations, might be one of the most enduring misconceptions in all of science. The reality, as proposed by some of the most brilliant minds in cosmology, is far stranger and infinitely more subtle. The true birth of our cosmos may not have been a bang at all, but a silent, breathtakingly rapid unfurling of spacetime itself, an event so quiet its signature has been hiding in plain sight for nearly 14 billion years. This revolutionary idea is known as cosmic inflation, and it completely reimagines our cosmic origin story. Instead of a chaotic fireball, picture this, a seed of reality, unimaginably small and dense, experiencing a trigger that caused it to expand faster than the speed of light. In less than a trillionth of a second, the universe we inhabit grew from smaller than a single proton to something perhaps the size of a grapefruit. This wasn't an explosion into space, this was space itself stretching at a rate that defies intuition. Because there was no air to carry sound waves in that primordial void, this monumental event would have occurred in utter silence. There was no boom, no roar, just the silent, rapid inflation of the fabric of reality. The architect of this groundbreaking theory was physicist Alan Guth. Back in the 1980s, he was wrestling with several puzzles the standard Big Bang model couldn't solve, like why the universe appears so remarkably uniform in every direction we look. His flash of insight that a period of super-fast expansion could smooth everything out was nothing short of revolutionary. He famously wrote in his notebook that it looked like a spectacular realization, and he was right. This idea of inflation elegantly explained not only the uniformity of the cosmos, but also its flatness, and the fact that we don't see any bizarre relics like magnetic monopoles. Andre Linde, another key figure, soon expanded on Guth's work, developing what's known as chaotic inflation theory. He proposed that this inflationary expansion might not be a one-time event but a perpetual process happening in different pockets of a much larger, eternal multiverse. This wasn't just a tweak to the model, it was a profound shift in perspective, suggesting our entire universe could be just one bubble in a vast cosmic foam, quietly inflating into existence. This theory moved the origin of everything from a singular, violent event to a potentially smooth, silent, and ongoing process. So why does this matter for those faint echoes we're searching for? Because inflation didn't just stretch space, it stretched the very quantum fluctuations that were present at that tiny scale. Those microscopic ripples were magnified to astronomical proportions, becoming the gravitational seeds for everything that followed: the galaxies, the stars, the planets. The theory predicts that this event would have also generated primordial gravitational waves, ripples in space-time that should still be washing through the universe today, carrying with them the faintest imprint of that silent beginning. Understanding this shift from a bang to a whisper is the essential first step in learning how to listen for its reverberations, a quest that takes us from the largest telescopes on Earth to the furthest edges of theoretical physics. But if the Big Bang was silent, how can we possibly hear its echoes? The answer lies in a hidden language woven into the very fabric of the cosmos, a symphony of frequencies so far beyond our natural perception that we've only just begun to develop the tools to translate them. This isn't a language of sound as we know it, but of vibration. It's the subtle tremor of space-time itself, the faint hum left over from creation, a cosmic code carrying secrets from the very first moments of time. Think of it like this: a dog whistle produces a sound that is completely inaudible to human ears, yet it's undeniably real and carries a clear signal to those who can perceive it. The universe is filled with the equivalent of cosmic dog whistles: gravitational waves, primordial vibrations, and quantum signals, all broadcasting information on frequencies we are biologically deaf to. This hidden language is written in the language of gravity and quantum mechanics. The most profound of these signals are gravitational waves, ripples in the four-dimensional fabric of spacetime predicted by Einstein over a century ago. Imagine spacetime as a still, silent pond. The Big Bang, or more specifically, the inflationary period that followed, was like a colossal pebble dropped into that pond. The impact itself might have been silent, but it sent out ripples that have been traveling across the pond ever since. These ripples are the primordial gravitational waves, and they carry an imprint of that initial event, a snapshot of the universe when it was less than a trillionth of a second old. They are the universe's oldest possible recording, and they are washing through you and everything around you at this very moment. Another crucial part of this cosmic dialect comes from the bizarre world of quantum physics. During that intense inflationary period, the universe was a seething sea of quantum fluctuations, tiny, random variations in energy that flickered in and out of existence. As inflation stretched the cosmos to an enormous size, it also stretched these microscopic quantum jitters, magnifying them into macroscopic ripples in density. These ripples became the gravitational seeds for everything we see in the night sky. Where there was a slightly denser patch of this primordial soup, gravity pulled in more matter, eventually forming galaxies and clusters of galaxies. The entire cosmic web, every star, every planet, every structure owes its existence to these amplified quantum whispers from the dawn of time. For decades, this was all beautiful theory. The challenge was building an instrument sensitive enough to actually listen for these whispers. That's where visionaries like Kip Thorne and the monumental effort behind the LIGO Observatory come in. LIGO, which stands for the Laser Interferometer Gravitational Wave Observatory, is essentially the most sensitive ear ever constructed by humanity. It doesn't listen for sound waves in the air, but for the infinitesimally small stretching and squeezing of spacetime caused by passing gravitational waves. The detectors are so precise they can measure a distortion 10,000 times smaller than the nucleus of an atom, the equivalent of measuring the distance to the nearest star with an accuracy the width of a human hair. When LIGO made its first historic detection in 2015, it wasn't of the primordial waves from the Big Bang, but of two black holes colliding over 1 billion light-years away. That event sent a chirp, a literal vibration in space-time, across the universe, which LIGO instruments successfully recorded. This was the moment we truly learned to hear the universe in a whole new way, confirming that this hidden language of gravitational waves was real and decipherable. Researchers describe the feeling of that first detection as one of awe and profound humility, finally tuning into a cosmic conversation that has been ongoing for billions of years. The technology is now advancing at a breakneck pace, with space-based detectors like LISA planned for the future, which will be quiet enough to potentially hear the faint, low-frequency hum of those primordial waves from the universe's birth. Decoding this hidden language is the key to unlocking the universe's deepest mysteries. These unheard frequencies could tell us what powered inflation, what the universe was like before the Big Bang, and even reveal the existence of extra dimensions of space. They are a direct line to the very beginning, a form of cosmic archaeology that allows us to dig deeper into time than any telescope ever could. By learning to listen to these whispers, we are not just expanding our senses, we are beginning to read the foundational code of reality itself, a code written in vibrations that have been echoing silently through the cosmos since the very first moment. So what exactly are these ripples in the fabric of reality? Gravitational waves are not waves of sound or light. They are literal distortions in the four-dimensional canvas of spacetime itself. Imagine the universe as a taut, flexible rubber sheet. When a massive object like a star or a black hole moves or accelerates, it creates a disturbance in that sheet, much like a spinning bowling ball would send ripples across its surface. These ripples are gravitational waves, and they propagate outward at the speed of light, stretching and squeezing everything in their path as they travel across the cosmos. They are an inescapable consequence of Einstein's general theory of relativity, which tells us that mass and energy tell spacetime how to curve, and that curved spacetime tells matter how to move. For a century, these waves remained a purely theoretical prediction. The distortions they cause are so incredibly tiny that Einstein himself doubted we would ever have the technology to detect them. The Laser Interferometer Gravitational Wave Observatory, or LIGO, proved him wrong. This monumental achievement in science and engineering consists of two identical observatories, one in Washington State and one in Louisiana, separated by nearly 2,000 miles to rule out local false alarms. Each facility boasts two arms, each 2.5 miles long, arranged in a perfect L shape. Inside these vacuum tubes, scientists fire lasers down the arms to precisely measure their length. When a gravitational wave passes through Earth, it minutely distorts space itself, making one arm imperceptibly longer and the other shorter, before then reversing the effect. This tiny change, a fraction of the width of a proton, is what LIGO was designed to measure. The morning of September 14, 2015, is now etched in scientific history. After decades of design, construction, and increasing the detector's sensitivity, LIGO recorded a signal that would change astronomy forever. The data showed a distinctive chirp, a rising frequency that matched almost perfectly with Einstein's equations for the final moments of two massive black holes spiraling inward and merging into one. This event occurred over 1 billion light-years away, and the ripple it created spent all that time traveling across the universe before finally being caught by our humble detectors. The signal was so clear and strong that researchers described the moment of discovery with a sense of awe and disbelief. We had, for the very first time, directly heard the universe speak to us through the medium of gravity itself. This discovery opened up an entirely new sense for exploring the cosmos, a field now known as gravitational wave astronomy. Before this, our view of the universe was almost entirely based on light, from radio waves to visible light to gamma rays. But light can be blocked, absorbed, or scattered by dust and gas. Gravitational waves, being ripples in spacetime itself, pass through matter almost completely unimpeded. This allows us to peer into regions of the universe that were previously invisible, like the immediate environment around black holes or the incredibly dense cores of neutron star collisions. Each type of cataclysmic event creates its own unique waveform, a specific pattern of ripples that acts like a cosmic fingerprint, telling us exactly what kind of event caused it and how massive the objects were. The most exciting development from this new sense is multi-messenger astronomy, where we observe the same event using both gravitational waves and traditional telescopes. The pinnacle of this effort came in August 2017, when LIGO detected the ripples from two neutron stars colliding. Just seconds later, space-based gamma-ray telescopes saw a flash of light from the same patch of sky. This triggered a massive global campaign, with astronomers around the world pointing every available telescope at that point in space. They observed the aftermath in every wavelength of light, witnessing the creation of heavy elements like gold and platinum in real time. This single event connected the distortion of spacetime to the very stuff we are made of, proving that the gold in a wedding ring or the uranium in a power plant was forged in the unimaginable violence of a neutron star merger, an event we detected first by feeling its ripples in spacetime. While we have now heard the crashes of black holes and the collisions of neutron stars, the holy grail of this field remains detecting the primordial gravitational waves generated by inflation itself. These waves would form a constant, low-frequency hum permeating all of space, a fossil imprint from the universe's silent birth. Current ground-based detectors like LIGO are not sensitive to these low frequencies, as they are drowned out by seismic noise and other earthly vibrations. The future of this search lies in space. The Laser Interferometer Space Antenna, or LISA, is a planned mission that would create a gravitational wave observatory in the quiet vacuum of space, with 3 spacecraft flying in a giant triangular formation millions of miles apart. By precisely measuring the distance between them with lasers, LISA would be able to tune into the low-frequency gravitational symphony, potentially hearing the faintest whisper of all the echo of the Big Bang itself. This would be the ultimate confirmation of inflation and provide a direct glimpse into the very first moments of existence, a secret the universe has been keeping for nearly 14 billion years. But if gravitational waves give us a new way to hear the cosmos, there is another, even older messenger that allows us to see the universe in its infancy. This is the cosmic microwave background radiation, the oldest light in existence. It is the afterglow of the Big Bang itself, a fossilized snapshot of the universe when it was a mere 380,000 years old, a cosmic baby picture. Before this moment, the universe was too hot and dense for light to travel freely. It was a searing, opaque fog of plasma, where photons were constantly bouncing off free electrons. But as the universe expanded and cooled, electrons combined with protons to form the first neutral atoms. In an instant, the fog cleared. The light that had been trapped within that plasma was suddenly set free, and it has been traveling across the cosmos ever since, cooling and stretching with the expansion of the universe until it reaches us today as a faint microwave static. This discovery was one of the greatest accidents in scientific history. In the 1960s, two astronomers at Bell Labs, Arno Penzias and Robert Wilson, were troubleshooting a persistent, annoying hiss in a giant radio antenna they were using for communications research. No matter what they did cleaning out pigeon droppings, checking for electrical interference, this faint, uniform microwave noise persisted from every direction in the sky. They had inadvertently stumbled upon the CMB, the cooled remnant of the universe's fiery birth. This discovery provided the first strong evidence for the Big Bang theory and earned them a Nobel Prize. It was the ultimate cold case, a piece of evidence from the beginning of time that had been hiding in plain sight, masquerading as technical static. The true treasure of the CMB, however, is not its uniformity but its tiny imperfections. To the naked eye, the map of this ancient light looks like a nearly perfect, smooth blanket of microwave radiation. But when we look with exquisitely sensitive instruments, we see that it is not perfectly uniform. It is filled with minuscule variations in temperature, tiny hotspots and cold spots that differ by only millionths of a degree. These are the anisotropies, and they are the most important fingerprints we have from the early universe. These tiny fluctuations are not random noise. They are the imprints of the quantum seeds that inflation stretched to cosmic size. They represent the slight over-densities and under-densities in the primordial plasma that would, over billions of years, become the gravitational wells that pulled matter together to form galaxies, stars, and ultimately us. Unlocking the secrets encoded in this pattern required a new generation of space telescopes. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, was the first mission to create a detailed, full sky map of these subtle temperature variations. Its data was revolutionary, allowing cosmologists to measure the age, composition, and geometry of the universe with unprecedented precision. It told us the universe is 13.8 billion years old, that ordinary matter makes up less than 5% of it, and that the geometry of the cosmos is flat to an astonishing degree of accuracy. WMAP provided the foundational data that cemented our standard model of cosmology, but the quest for even greater detail continued with the Planck satellite, a European Space Agency mission that launched in 2009. Planck was the most advanced CMB mapper ever built, with sensitivity so high it could discern temperature variations finer than a millionth of a degree. Astronomer George Smoot, who won a Nobel Prize for his earlier CMB work, described the map produced by Planck as like going from a standard definition television to ultra-high definition. The intricate patterns revealed were a perfect match for the predictions of inflationary theory, showing the specific statistical signature of quantum fluctuations that had been magnified by the universe's rapid expansion. John Mather, another Nobel laureate for his work on the CMB, has called it the blueprint for the universe, a direct link back to the quantum seeds planted during the first moments. The most tantalizing goal of these missions has been to find within this blueprint the faint signature of primordial gravitational waves. These waves would have left a distinct curling pattern in the polarization of the CMB light, known as B modes. Finding this pattern would be the smoking gun for inflation, direct evidence of the universe's violent, silent birth. While there have been tantalizing hints, like the controversial BICEP 2 announcement in 2014 that was later attributed to interstellar dust, a definitive detection remains elusive. The search continues with ever more sensitive experiments, because finding that signal would allow us to peer back to an almost incomprehensibly early time, to the very moment when the largest structures we see today were smaller than a single subatomic particle. The cosmic microwave background is more than just ancient light. It is a time capsule, a message from the dawn of time, and we are still learning how to read every last whisper it contains. Now, the search for these primordial gravitational waves brings us to one of the most exciting and technically daunting challenges in all of modern cosmology. If we could actually detect these ripples, it would be like finding the original fingerprint on the cosmic crime scene, the ultimate proof that the universe underwent that fantastic period of inflationary expansion. But how do you find a fingerprint that is nearly 14 billion years old and imprinted on the entire sky? The answer lies in a very specific and subtle pattern hidden within the oldest light we can see, the cosmic microwave background. This is where the concept of polarization comes in. Light, as you might know, can be thought of as a wave that vibrates in a particular direction. When this light scatters off particles, like the electrons in the early universe's plasma, it can become polarized, meaning its waves are preferentially oriented in a certain direction. The gentle compression and rarefaction waves moving through the hot plasma of the early universe created a straightforward, curl-free pattern of polarization in the CMB, known as E-modes. These were detected years ago and gave us a wealth of information, but the real treasure, the signal from primordial gravitational waves, would create a completely different kind of pattern, one with a curling, twisting quality. These are called B-modes, named after a mathematical property similar to magnetic fields, and they are the specific fingerprint we are desperately searching for. The reason these B-modes are so important is that they would have been generated in a unique way. As those primordial gravitational waves, born from inflation, rippled through the fabric of space-time in the universe's first instant, they would have physically jiggled the plasma. This jiggling would have imparted a distinct, swirling signature to the polarized light, a pattern that simply cannot be created by the density fluctuations alone that gave us the E-modes. Finding this specific curl in the polarization of the CMB is considered the smoking gun for inflation. It's a direct line back to an era of unbelievable energy, a time when gravity itself was a quantum force, and it would tell us not just that inflation happened, but how much energy was involved, giving us clues about the physics that operated at those unimaginable scales. The quest to find these B-modes has been a story of incredible ambition, cutting-edge technology, and heartbreaking setbacks. It's a mission that has required going to some of the most extreme environments on Earth. High atop the Antarctic Plateau at the South Pole sits a telescope called BICEP, the background imaging of cosmic extragalactic polarization. Why Antarctica? The air there is incredibly cold, dry, and stable, offering a crystal-clear window to observe the faint microwave whispers from the cosmos. The BICEP project and its more advanced successors like the Keck array are essentially custom-built, ultra-sensitive polarimeters designed to stare at a single, exceptionally clean patch of sky for years on end, meticulously measuring the subtle polarization of the CMB photons that have been traveling for over 13 billion years. The excitement in this field reached a fever pitch in 2014. The team behind the BICEP 2 telescope, led by researcher Ko Lin Kuo, held a press conference that sent shockwaves through the scientific community and made headlines around the world. They announced with great confidence that they had detected the telltale B-mode polarization, a signal they believed was from primordial gravitational waves. It was a moment of pure, unadulterated scientific euphoria. Kuo even famously surprised inflation theorist Andre Lind at his home with champagne to celebrate what seemed like a monumental confirmation of his life's work. For a brief, glorious period, it looked like we had finally heard the echo of the universe's birth, but the elation was short-lived. The scientific process, with its rigorous checks and balances, soon intervened. Other researchers, particularly those working with the European Space Agency's Planck satellite, pointed out a critical and complicating factor: galactic dust. Our own Milky Way galaxy is filled with microscopic grains of dust that are not only good at blocking starlight but are also magnetically aligned. This alignment causes them to emit their own polarized microwaves, creating a foreground, fog, that can perfectly mimic the curling B-mode pattern everyone was looking for. The BICEP 2 team had used a preliminary dust map from Planck to estimate this contamination, but the final, more detailed analysis revealed that the signal they saw could be entirely explained by this pesky interstellar dust. It was a devastating blow, a sobering reminder of how difficult it is to find an infinitesimally small signal buried under layers of cosmic noise. Yet this setback did not kill the search, it refined it. The collaboration that followed between the BICEP/Keck teams and the Planck mission is a beautiful example of how science self-corrects and moves forward. By combining their data, they could create a much clearer picture, effectively subtracting the dusty foreground to see what, if anything, remained beneath. The result was that the initial thrilling signal disappeared, but the upper limits they placed on the strength of the primordial gravitational wave signal were themselves profoundly important. They told us that if these waves are there, they are even fainter than we had hoped, which in turn tells us that the energy scale of inflation might be lower than some of the more dramatic theories predicted. The hunt is far from over. New generations of experiments are now coming online, each more sensitive than the last. Projects like the Simons Observatory and the ambitious SIMBI S4 are deploying arrays of telescopes with hundreds of thousands of detectors, capable of observing at multiple frequencies. This multi-frequency approach is the key to solving the dust problem, as dust glows brighter at certain frequencies than others, allowing scientists to isolate and remove its contaminating signal with surgical precision. The goal remains unchanged: to sift through the static of our own galaxy and find that primordial curl, the unmistakable signature of spacetime itself ringing from its silent, explosive birth. Finding it would be one of the greatest discoveries in human history, a direct observation of the universe's very first moment. But to truly grasp the origin of everything we see in the night sky, we must venture into the bizarre and counterintuitive realm of the quantum. The majestic cosmic web of galaxies, the vast voids between them, even the very planet we stand on, all of it can be traced back to the most ghostly, ephemeral phenomena imaginable: quantum fluctuations. These are not fluctuations in something, they are the something. In the vacuum of empty space at the tiniest scales, reality is not still and silent. It is a seething, bubbling foam where particles and energy flicker in and out of existence, borrowing energy from the future for fleeting moments before vanishing again. This isn't a theoretical curiosity. It's a fundamental property of our universe, a constant, low-level fizz at the heart of reality. During the inflationary period, this quantum fizz was everything. The entire observable universe was compressed into a space trillions of times smaller than a single proton, a realm where quantum effects weren't just important, they were the only effects. At that scale, the universe was a storm of these random energy fluctuations. And then, in a fraction of a nanosecond, inflation acted like a cosmic magnifying glass of unimaginable power. It took those infinitesimal quantum jitters regions that were a minuscule amount denser or less dense than their surroundings and stretched them across the cosmos. What was once a microscopic random variation became a macroscopic ripple in the density of the universe. A fluctuation that was smaller than a subatomic particle one moment became a region light years across the next, its subtle gravitational signature now frozen into the fabric of spacetime. This profound connection between the quantum world and the cosmic scale was a revolutionary insight, championed by physicists like Stephen Hawking and Alexei Starobinsky. They realized that inflation provided the perfect mechanism to promote these quantum seeds to classical, astronomical structures. Starobinsky, working on refining the theory of inflation, was among the first to calculate in detail how these quantum gravitational fluctuations would be amplified. Hawking, alongside others, helped demonstrate that the pattern of these stretched fluctuations would have a very specific signature, one that wasn't smooth, but followed a particular statistical distribution. This prediction was absolutely crucial. It gave cosmologists a specific pattern to look for in the cosmic microwave background. They weren't just looking for any imperfections, they were looking for the specific fingerprint of amplified quantum noise. And that is exactly what we found. The incredibly detailed maps from the Planck satellite reveal the ancient photons of the CMB are not perfectly uniform. They show tiny variations in temperature, differences of mere millionths of a degree. These hot spots and cold spots are the direct descendants of those primordial quantum density fluctuations. The hotter spots correspond to regions that were slightly denser after inflation. Their extra gravity pulled in more matter over billions of years. The colder spots correspond to the slightly emptier regions. This map is nothing less than a baby picture of the universe, and imprinted on it is the quantum blueprint for all future structure. Every galaxy cluster, every swirling nebula, every solitary star exists because of the gravitational pull initiated by these magnified quantum seeds. So the next time you look up at a star-filled sky, consider this incredible chain of events. The random, unpredictable dance of particles on a scale we can scarcely conceive set the gravitational traps that, over eons, collected the gas that would ignite into stars. Those stars forged the heavy elements in their cores that were later blasted across space in supernova explosions, providing the raw material for planets, oceans, and life itself. The carbon in your cells, the iron in your blood, the calcium in your bones, all were cooked in stars that only formed because of a microscopic quantum fluctuation in the first moment of time that got stretched into a cosmic destiny. We are not just living in a universe that has quantum mechanics, we are living in a universe that was built by it. The grandest structures in existence are, at their heart, the magnified echoes of quantum whispers. Yet for all its profound success in explaining the large-scale structure of the cosmos, our current model of the universe rests on a startling and humbling confession: we only understand about 5% of it. The ordinary matter that makes up stars, planets, and everything we can see and touch is just a tiny fraction of the cosmic inventory. The rest, the overwhelming majority of reality, is composed of two utterly mysterious and invisible components: dark matter and dark energy. These are not just minor details in our cosmic equations, they are the dominant forces shaping the universe's fate, and their nature remains one of the greatest unsolved puzzles in all of science. And now, a tantalizing new possibility is emerging. What if these dark components are not just invisible, but are somehow intimately connected to those primordial frequencies, the unheard echoes from the silent Big Bang? Let's start with dark matter. We cannot see it, we cannot touch it, and it does not interact with light in any way. So how do we even know it's there? The evidence comes from its immense gravitational pull. In the 1930s, a brilliant astronomer named Fritz Zwicky was studying the Coma cluster, a giant group of galaxies. He calculated how much mass the cluster should have based on the visible light from its stars. Then he calculated the mass needed to provide the gravity that was holding these rapidly moving galaxies together. The two numbers didn't just disagree, they were catastrophically different. The gravitational mass was hundreds of times greater than the visible mass. Zwicky proposed the existence of dunkle materie, or dark matter, to account for this missing mass. decades later, the work of Vera Rubin provided even more compelling proof. She meticulously measured the rotation speeds of stars within spiral galaxies. According to the laws of gravity, stars on the outer edges of a galaxy should orbit much more slowly than those near the center. But Rubin found that they all orbit at roughly the same speed. The only explanation is that each galaxy is embedded within a massive, invisible sphere of matter, a dark matter halo whose gravity is whipping the outer stars around far faster than the visible matter alone could. For decades, the leading hypothesis has been that dark matter is made of some kind of slow-moving, exotic particle that barely interacts with normal matter. These hypothetical particles are often called WMAP, or weakly interacting massive particles. Countless experiments have been built deep underground, in abandoned mines and tunnels, hoping to catch the extremely rare flicker of a WMAP bumping into an atomic nucleus. So far, they've all come up empty. This has led physicists to consider other, even more exotic possibilities. One of the most intriguing is a particle called the action. Theorized to solve a different problem in particle physics, actions would be incredibly light, trillions of times lighter than an electron, and they would behave less like discrete particles and more like a pervasive, invisible field that permeates all of space. And here's where the connection to cosmic echoes gets fascinating. Because actions are so light and wave-like, they could have been produced in vast quantities during those first chaotic moments of the universe. Some theories suggest they would have a specific preferred frequency. This means the dark matter holding our galaxy together might not be a cloud of particles, but a coherent, vibrating field, an unheard frequency ringing through the cosmos since its inception. Detecting this specific frequency would not only reveal the identity of dark matter, but would also provide a direct window into the physics of the early universe. If dark matter is the mysterious glue holding galaxies together, dark energy is the even more baffling force that is tearing the entire cosmos apart. Its story begins in the late 1990s when two teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were measuring the distances to faraway supernova. They expected to find that the expansion of the universe, set in motion by the Big Bang, was gradually slowing down due to the pull of gravity. Instead, they made the shocking discovery that the expansion is actually accelerating. Something was counteracting gravity and pushing galaxies apart from one another at an ever-increasing rate. This something was dubbed dark energy. Perlmutter described the finding as utterly surprising, saying it was like throwing a ball into the air and watching it not only fail to come down but instead shoot off into the sky at an ever faster speed. This discovery turned cosmology on its head and earned them the Nobel Prize. What could dark energy be? Einstein himself provided one possible, though controversial, answer. He once introduced a fudge factor into his equations called the cosmological constant, a repulsive energy inherent to the fabric of empty space itself. He later called it his greatest blunder, but modern discoveries suggest he may have been right for the wrong reason. If dark energy is indeed the cosmological constant, it means that empty space is not nothing. It has a fundamental energy density that causes it to push outward. But this leads to a huge problem. When physicists try to calculate how strong this energy should be based on quantum theory, their answer is wrong by a factor of 1 followed by 120 zeros. It is arguably the worst prediction in the history of science. This colossal failure suggests we are missing something deep and fundamental about the nature of spacetime. Perhaps dark energy isn't a constant at all, but a dynamic field that has changed over the life of the universe. Some theories even propose a connection to those primordial frequencies, suggesting that the same inflationary field that drove the universe's rapid expansion didn't vanish but simply faded into the background, its residual energy manifesting today as the subtle, repulsive force of dark energy. The potential link between these dark components and the universe's first moments is what makes the search for cosmic echoes so critically important. If dark matter is made of actions, then sophisticated experiments like the Action Dark Matter experiment are essentially trying to tune a radio to the specific frequency of this invisible matter. If dark energy is a dynamic field, its vibrations might leave a faint imprint on the large-scale structure of the universe, a pattern that could be detected by future galaxy surveys. Unraveling the mysteries of dark matter and dark energy is not just about identifying what's out there. It's about completing our understanding of cosmic evolution, from the silent whisper of inflation to the formation of galaxies and ultimately to the fate of everything. The echoes we are trying to hear may be the key to deciphering the dark 95% of reality, revealing that the universe's silent beginning continues to shape its destiny in ways we are only beginning to imagine. But if the nature of our own universe is strange enough, the next idea takes us into territory that is truly mind-bending. What if our entire cosmos, with all its hundreds of billions of galaxies and its dark, mysterious components, is not the only one? What if it is just one bubble in a vast, frothing cosmic ocean of universes, each with its own unique set of physical laws? This is the Multiverse Hypothesis, and it pushes the boundaries of cosmology from the incredibly vast to the almost incomprehensible. It's a concept that springs naturally from the theory of eternal inflation, suggesting that the rapid expansion that shaped our universe wasn't a one-time event, but an endless process, continuously giving birth to new universes in a meta-cosmic landscape beyond our own. The mechanism for this is as elegant as it is staggering. Imagine the inflationary field, the energy that drove the universe's exponential growth, as a landscape of rolling hills. In most places, this field has rolled down into a valley, its energy spent, allowing for the formation of stars and galaxies as we know it. This is our universe. But according to theorists like Andre Lind, in other regions, this field might still be perched high on a hilltop, retaining its immense energy and continuing to inflate at a fantastic rate. In these regions, space-time is stretching so fast that pockets of it pinch off, forming self-contained bubbles of reality. Each of these bubbles is a separate universe, potentially with completely different fundamental constants. In one, the force of gravity might be stronger, preventing atoms from ever forming. In another, the nuclear forces might be weaker, so no stars ignite. Our universe, with its seemingly fine-tuned laws that allow for our existence, could be just one rare bubble where the dice landed perfectly for life. This leads us directly to one of the most profound questions in all of science. Could we ever find evidence for these other realms? If they are truly separate universes, existing in their own dimensions of space-time, the answer would seem to be a definitive no. But some of the most brilliant minds in physics are exploring a tantalizing possibility. Perhaps these other universes didn't form in perfect isolation. In the frenetic energy of the earliest moments, as our bubble universe was first inflating, a neighboring bubble might have collided with ours. Physicist Max Tegmark has categorized different levels of the multiverse, and this concept of a bubble collision falls into what he calls a level Roman II multiverse. Such a collision would have been a cataclysmic event, sending ripples through the very fabric of our young cosmos, leaving a permanent scar or a distinct pattern in the ancient light of the cosmic microwave background. This is where our search for unheard frequencies takes on a whole new dimension. the gravitational waves or density variations from such an inter-universal collision would have left a specific, anomalous signature, a kind of cosmic bruise. Researchers have meticulously scoured the Planck satellite's map of the CMB, looking for any strange, circular patterns or unexpected cold spots that could be the trademark of such an event. While no definitive evidence has been found, the search continues. Finding such a pattern would be arguably the most significant discovery in human history. It would be empirical proof that our universe is not alone, that there is a beyond. It would transform cosmology from the study of our one universe to the study of the multiverse, a meta-cosmology that would forever change our place in the grand scheme of things. The multiverse idea also finds a comfortable home in string theory, which is itself an attempt to unify all the forces of nature. String theory proposes that the fundamental building blocks of reality are not point-like particles but tiny, vibrating strings. The way these strings vibrate determines the properties of the particles they manifest, as much like different vibration patterns on a violin string produce different musical notes. But for the math to work, string theory requires extra dimensions of space, many more than the three we experience. These extra dimensions are thought to be curled up into intricate, tiny shapes called Calabi-Yau manifolds. The specific way they are curled determines the physical laws of that universe, like the tuning of a complex instrument. This gives rise to the concept of the string theory landscape, an idea popularized by physicist Brian Greene. This landscape is a vast, higher-dimensional realm of possible universes, each with its own unique geometry for those extra dimensions, and therefore its own unique set of physical constants. The number of possible configurations is astronomical, perhaps around 10 to the power of 500. In this unimaginably vast landscape, our universe, with its specific laws, is just one possibility. The silent Big Bang, in this view, was the moment our particular bubble of space-time, with its specific tuning, crystallized out of this landscape. The primordial frequencies we are searching for, then, might not just be echoes from our beginning, but whispers from the broader multiverse, faint signals encoded with information about the wider cosmic reality from which we emerged. The philosophical implications are enough to make your head spin. It challenges the very definition of what is real and what is knowable. If the multiverse is real, then every possible outcome happens somewhere. There are universes where you never existed, and perhaps others where every choice you made branched off into a different reality. It turns the fine-tuning of our universe from a miraculous mystery into a simple selection effect. We can only exist in a universe whose laws allow for our existence, so it's no surprise we find ourselves in one. While this idea can feel unsettling, making our universe seem less unique, it also paints a picture of a reality of boundless creativity and infinite possibility. The search for those faint echoes, those whispers from other realms, is ultimately a search for our own cosmic context, a desperate attempt to listen for the neighbors in a reality we are only beginning to realize might be the busiest street in the metacosmos. Yet for all its mathematical beauty, string theory presents us with a truly radical reimagining of reality's most basic ingredients. Forget the idea of a universe built from tiny, solid, point-like particles. Instead, picture the fundamental bedrock of everything, every electron, every quark, every force-carrying photon, as an unimaginably small, vibrating loop of energy. These are the strings of string theory, and their behavior dictates everything we see. The only difference between one particle and another is the specific way its string vibrates. An electron isn't a tiny ball, it's a string vibrating at one particular frequency. A photon is that same type of string, but vibrating in a completely different pattern. In this view, the entire universe is a vast cosmic symphony, and the properties of matter and energy are simply different musical notes played on these tiny, fundamental strings. This elegant idea becomes even more powerful when we consider its ultimate ambition, to be a theory of everything. For decades, physics has been grappling with a deep schism. We have two incredibly successful but utterly incompatible frameworks. Quantum mechanics describes the bizarre, probabilistic world of the very small with breathtaking accuracy. Einstein's general relativity describes the force of gravity and the nature of space-time on large scales perfectly, but the two theories refuse to talk to each other. They break down when you try to apply them to the same extreme conditions, like the center of a black hole or the first moment of the Big Bang. String theory is the most promising candidate we have for bridging this divide. It naturally incorporates gravity by including a specific string vibration that perfectly matches the properties of the hypothetical graviton, the particle that would carry the gravitational force. For the first time, gravity is not a foreign concept awkwardly forced into a quantum world. It is an intrinsic and inevitable part of the theory's melody. The profound connection to our main story emerges when we ask a simple question. Where did these vibrational patterns come from? Could the specific frequencies that define the particles in our universe today have been set during those first moments of cosmic inflation? It's a possibility that excites theorists like Edward Witten, a central figure in the development of string theory. The immense energy of the inflationary period would have been more than enough to excite these fundamental strings into their various vibrational states, essentially tuning the cosmic instrument. The frequencies we observe in particles today could be fossil vibrations, echoes of that initial energetic pluck that have been resonating unchanged for nearly 14 billion years. The silent Big Bang may not have been completely silent after all on this stringy scale. It may have been a moment of intense, multidimensional music whose opening chords still determine the fundamental laws of physics. To make the math of string theory work, it demands something extraordinary, extra dimensions of space. We are familiar with the three dimensions of length, width, and height. String theory suggests there are actually 6 or 7 additional spatial dimensions, but they are curled up into a space so infinitesimally small that we never perceive them. The physicist Michio Kaku often uses a helpful analogy. Imagine a garden hose stretching off into the distance. From far away, it looks like a simple one-dimensional line. But if you could shrink down to the size of an ant and crawl on its surface, you would discover it has a second dimension, a circular dimension going around its circumference. The extra dimensions of string theory are thought to be curled up in a similar way, but into incredibly complex, multi-dimensional shapes known as Calabi-Yau manifolds. The specific geometry of these hidden dimensions is what ultimately determines the possible vibrational frequencies of the strings. It sets the tuning of the entire cosmic orchestra. This leads to an almost philosophical conclusion about the nature of our reality. The universe isn't just described by mathematics. In a very real sense, it is mathematics. The vibrational patterns, the geometry of hidden dimensions, the symphony of strings, these are all mathematical structures. The search for the fundamental laws of physics becomes a search for the unique mathematical consistency that allows for a stable, complex universe like our own to exist. The primordial frequencies we've been discussing, whether in the form of gravitational waves or quantum fluctuations, might be the audible manifestations of this deeper, underlying mathematical harmony. We are not just listening to the echoes of an event, we might be deciphering the foundational code of reality, written in the language of vibration and heard across the expanse of space and time. This concept of a universe built on vibration leads us to a powerful and elegant principle that might be operating on the grandest of scales: resonance. We encounter resonance in our everyday lives. An opera singer shatters a glass by hitting the exact note it naturally vibrates at, or a child on a swing soars higher with perfectly timed pushes. It's the phenomenon where one vibrating object transfers its energy most efficiently to another when their frequencies match, creating a synchronized, amplified effect. Now imagine that same principle, but applied to the cosmos itself. What if the faint, primordial frequencies generated during the universe's birth are still humming through space-time, and their vibrations are synchronizing with and shaping the structures that form within it, from the spin of galaxies to the orbits of planets, creating a kind of cosmic harmony that brings order out of initial chaos? We can see clear, beautiful examples of this mechanical resonance at work right here in our own solar system. Look at Neptune and Pluto. For every 3 complete orbits that Neptune makes around the Sun, Pluto makes exactly 2. This stable, repeating ratio is a gravitational resonance. Their orbital periods are synchronized, locked in a rhythmic dance that prevents them from ever colliding or being flung into different paths. The moons of Jupiter exhibit this same phenomenon, with Ganymede, Europa, and Io locked in a 1-2-4 orbital resonance that keeps their orbits stable and generates intense tidal heating within them, perhaps even creating the subsurface oceans that make them prime targets in the search for extraterrestrial life. These aren't just random coincidences, they are the natural outcome of gravitational interactions over billions of years, where objects find these stable, resonant frequencies that allow them to persist. It's the solar system tuning itself. Now, expand that idea to the largest structures in the universe. The distribution of galaxies across the cosmos isn't entirely random. They are arranged in a vast cosmic web, with long filaments of galaxies connecting at dense nodes, surrounding enormous, empty voids. This intricate pattern emerged from those initial quantum fluctuations that were amplified during inflation. But some cosmologists propose that resonant effects might have played a role in sculpting this web. Certain primordial frequencies, specific vibrational modes from the early universe, could have preferentially amplified the growth of structures of a certain size. Where the frequency of the density waves matched the natural gravitational frequency for collapse on a particular scale, the formation of galaxy clusters would have been enhanced, much like a singer's sustained note encourages a specific glass to vibrate. The cosmic web itself, then, could be a frozen snapshot of resonance on a galactic scale. The physicist Paul Davies has often spoken about the elegance and harmony inherent in the laws of the universe, suggesting that the cosmos seems to be tuned for complexity and life. This cosmic harmony might be more than a metaphor. It could be a literal, physical process driven by these underlying vibrations. The idea that the silent Big Bang's echoes are still tuning the universe is a profound one. It suggests that the initial conditions set the fundamental frequencies, and everything that has happened since, the formation of stars, the spinning of galaxies, the very stability of solar systems, is an ongoing process of synchronization with that ancient rhythm. The universe isn't just expanding and evolving, it is, in a sense, ringing like a bell, and all structures within it are finding their place in the grand symphony. This principle might even extend into realms we are only beginning to explore, such as biology. The field of quantum biology investigates whether quantum effects, like coherence and tunneling, play a role in biological processes. While highly speculative, some researchers ponder if subtle, environmental frequencies, perhaps even those of a cosmic origin, could influence these delicate quantum systems. Could the resonant vibrations that helped form galaxies also play a role in the synchronization of cellular processes or even neural patterns? It's a fringe idea, but it highlights the pervasive power of resonance as a universal organizing principle, connecting the unimaginably large to the infinitesimally small through the common language of vibration. The echoes of the silent Big Bang might not only have built the stage for life, but could still be whispering cues to the players upon it. But to actually capture these whispers, to transform them from theoretical predictions into hard data, we need more than just brilliant ideas. We need technological wizardry on an almost unimaginable scale. The quest to listen to the cosmos is driving a revolution in precision engineering, pushing us to build ears so sensitive they can hear the universe breathing. This isn't about building bigger telescopes. It's about building smarter, quieter, and more stable instruments capable of detecting signals that are billions of years old and fantastically faint. We are entering a golden age of cosmic audiology, where a new generation of observatories, both on Earth and in space, are being designed to amplify our perception and finally tune into the universe's deepest frequencies. On the ground, the work continues to make detectors like LIGO even more extraordinary. The current generation of these laser interferometers is already a marvel, but projects are underway for a massive upgrade. The next phase, known as the Advanced LIGO Plus project, aims to increase its sensitivity by another factor of 2 or more. This involves a suite of breathtaking innovations, from using more powerful lasers and heavier, purer mirrors to employing a technique called quantum squeezing. Quantum squeezing is a brilliant workaround for a fundamental limit imposed by the laws of quantum mechanics, themselves the Heisenberg uncertainty principle. This principle creates a faint, underlying quantum noise that can mask the weakest signals. By essentially shifting this uncertainty from a property that affects the measurement to one that doesn't, scientists can squeeze the noise down, allowing them to hear fainter gravitational waves. It's like silencing the subtle hiss on a recording to hear a whisper that was always there underneath. Yet, even the most advanced ground-based detectors have a fundamental limitation. They cannot listen to the lowest frequencies of the gravitational wave spectrum. The constant rumble of the Earth's microscopic seismic vibrations, the distant crash of ocean waves, even the hum of human activity creates a low-frequency wall of noise that drowns out the cosmic bass notes. To hear the steady hum of supermassive black holes orbiting each other in the hearts of distant galaxies, or the primordial rumble from the Big Bang itself, we must go to the one place that is truly silent: space. This is the ambitious goal of the Laser Interferometer Space Antenna, or LISA, led by the European Space Agency with significant contributions from NASA. LISA is not a single telescope but a constellation of 3 spacecraft. They will fly in a perfect triangular formation, trailing behind Earth in its orbit around the Sun, with each side of the triangle measuring a staggering 2.5 million kilometers long. The principle is the same as LIGO firing lasers between endpoints to measure tiny changes in distance, but the scale and environment are utterly different. Freed from Earth's noise, LISA arms will be millions of times longer, allowing it to detect gravitational waves with wavelengths far too long for any ground-based instrument. It will open up the low-frequency gravitational window for the first time, listening to the slow, stately dance of millions of binary systems within our own galaxy and the mergers of the very first supermassive black holes in the early universe. More importantly for our search, it will be our best shot at detecting the stochastic background of gravitational waves from inflation, the faint, omnidirectional hum that would be the definitive echo of the universe's silent birth. The technological challenges are immense, requiring flawless precision formation flying and the development of near-perfect free-falling test masses inside each spacecraft, but the potential payoff is a completely new symphony of cosmic sound. While LISA listens for ripples in space-time, other observatories are training their eyes on the ancient light of the cosmos with unprecedented clarity. The James Webb Space Telescope, though not a gravitational wave detector, plays a crucial supporting role in this grand investigation. By peering back to the very first galaxies, it helps us understand the sources of the gravitational waves that LISA will later detect. Seeing those early supermassive black holes and the galaxies they anchor provides the context for the waves they generate. It's the difference between hearing a loud crash in another room and then walking in to see exactly what fell over. The two senses together create a complete picture. JWST's incredible infrared vision is allowing us to map the cosmic structures that grew from those initial quantum seeds, providing a stunning visual complement to the gravitational soundtrack we are trying to hear. Beyond these colossal projects, a host of other innovative technologies are joining the hunt. Atomic interferometry uses the wave-like nature of atoms themselves as exquisitely sensitive probes for measuring tiny distortions. Experiments are proposed that would use clouds of ultra-cold atoms in space to detect gravitational waves in a completely different way. There are even plans to use the precise, regular pulses from distant neutron stars called pulsars as a natural galactic scale interferometer. By meticulously timing the arrival of these pulses from an array of pulsars across the Milky Way, astronomers hope to detect the subtle stretching and squeezing of spacetime as long wavelength gravitational waves pass through our galaxy. This pulsar timing array approach is like using the galaxy itself as a scientific instrument. None of these awe-inspiring advancements happen in isolation. They are the result of decades of painstaking work and international collaboration, a point powerfully emphasized by Nobel laureate Barry Barish, one of the key figures behind LIGO's success. He often speaks of the unbelievably talented people from all over the world, engineers, physicists, computer scientists, and technicians who pooled their expertise to make the impossible possible. These projects represent a monumental human achievement, a testament to our species' relentless curiosity and our ability to work together to solve profound mysteries. Each new technological leap brings us closer to answering the most fundamental questions about our existence, turning the philosophical whispers of a silent beginning into the measurable data that will define our understanding of the cosmos for generations to come. Even with the most advanced instruments ever built, the data they collect is never a clean, clear signal. It is a chaotic symphony of noise, the faint whisper of a gravitational wave from a billion light-years away, or the subtle temperature variation in the cosmic microwave background from the dawn of time, is buried under a mountain of static. Isolating that one true cosmic note from the cacophony is perhaps the single greatest technical challenge in all of modern cosmology. It is the ultimate game of finding a needle in a haystack, except the haystack is the size of the universe and the needle is a vibration smaller than an atom. This is where the painstaking, unglamorous work of data analysis and signal processing begins, a digital archaeology that sifts through terabytes of noise to uncover the echoes of creation. The first and most fundamental tool in this toolkit is a mathematical technique developed over 200 years ago, Fourier analysis. Named after the French mathematician Joseph Fourier, this process is a brilliant way to decompose any complex signal, no matter how messy, into its constituent pure frequencies. Imagine an entire orchestra playing at once. Your ear hears a single, complex wall of sound. Fourier analysis is like having perfect pitch for every instrument simultaneously. It can isolate the specific note played by the violin, the trumpet, and the timpani, telling you exactly how loud each one is. Cosmologists use this same principle on their data. They take the raw signal from a telescope like Planck or the strain data from LIGO and run it through a Fourier transform. This breaks the messy timeline of data into a spectrum of frequencies, a mountain range where each peak represents a signal at a specific pitch. The hope is that amidst the jagged landscape of random noise, a single, sharp, unexpected peak will emerge, the signature of a true cosmic event. But the universe is a messy place, and our own instruments are imperfect. The data is contaminated with what scientists call foregrounds and systematics. For the cosmic microwave background, the biggest foreground contaminant is the dust in our own Milky Way galaxy, which emits polarized microwaves that can perfectly mimic the primordial B-mode signal researchers are desperately seeking. For gravitational wave detectors like LIGO, the foreground noise is everything from the rumble of a distant truck to the microscopic thermal vibrations of atoms in the detector's mirrors themselves. Distinguishing a real cosmic signal from these artifacts requires more than just Fourier analysis. It requires a deep understanding of every possible source of noise. Teams will spend years meticulously building and updating what they call a noise budget, a comprehensive model that accounts for every known squeak, creak, and rumble their instrument could possibly produce. Any candidate signal that matches something already in the noise budget is immediately suspect. The real prize is something that doesn't fit, a signal that stands out from the modeled noise in a statistically significant way. This is where modern technology, specifically machine learning, is revolutionizing the field. The algorithms used in projects like LIGO are now trained on enormous libraries of simulated data. Scientists create millions of fake signals, digital injections of hypothetical gravitational waves from black hole mergers, and bury them in even more millions of simulated noise records. They then task powerful machine learning networks to learn the difference between the patterns of a true signal and the patterns of pure noise. These neural networks become incredibly adept pattern recognizers, often spotting the subtle chirp of a gravitational wave far more efficiently than traditional algorithms. However, this power comes with a caveat. As astrophysicist Jana Levin often points out, this process requires immense caution. A machine learning algorithm might be a black box. It can tell you that a signal is there, but not always why it decided that. The final validation always requires that the signal can be understood within the clear, testable framework of physical equations like Einstein's general relativity. The gold standard for a discovery in this field is a 5 sigma result, a statistical measure that indicates there is only a 1 in 3.5 million chance that the detected signal is a random fluctuation in the noise. Reaching this incredible level of certainty is a grueling process. For the first gravitational wave detection, the LIGO team spent months in a state of blind injection, where a small subset of engineers could secretly inject fake signals into the detector without the knowledge of the data analyst. This ensured that the analysts couldn't subconsciously bias their results, forcing them to develop rigorous, objective criteria for a detection before they even knew if they had one. When the real signal came in, it had to pass the exact same unforgiving tests. Every aspect of the signal, its shape, its strength, its frequency evolution, is compared against theoretical predictions. It must be seen in both of the widely separated LIGO detectors with the correct time delay for a wave traveling at the speed of light. This meticulous cross-checking and validation is what transforms an intriguing blip in the data into a world-changing scientific fact, ensuring that the whispers we hear are truly from the cosmos and not just the creaking of our own machinery. Yet for all the technological prowess of our detectors and the cleverness of our algorithms, we would be utterly lost without the one universal tool that allows us to interpret what we find. That tool is mathematics. It is the silent, abstract language that the universe itself seems to be written in, a code that allows us to translate the raw data of cosmic whispers into a coherent story of our origins. While our instruments gather the noise, it is mathematics that provides the grammar and syntax to find the signal, to decode the patterns hidden within the chaos, and hear the profound meaning in the universe's faintest echoes. This isn't just about using math as a calculator. It's about recognizing that the deepest laws of physics are fundamentally mathematical structures. The primordial gravitational waves we search for are described perfectly by wave equations, the same kind of differential equations that predict the motion of a guitar string or a ripple in a pond. The quantum fluctuations that seeded all galaxies are understood through the complex probabilities of quantum field theory. Even the mind-bending concept of curved spacetime in Einstein's general relativity is articulated not in words, but in the elegant, non-Euclidean geometry of tensors and manifolds. Mathematics is the native tongue of the cosmos, and to listen to its whispers, we must first become fluent in this language of symbols and symmetries. The power of this language is beautifully embodied in the work of mathematicians like Emmy Noether. In the early 20th century, she discovered a profound connection between symmetry and the conservation laws of physics, a principle now known as Noether's theorem. In simple terms, she proved that for every continuous symmetry in nature, there is a corresponding quantity that is conserved. The fact that the laws of physics don't change from day to day, a symmetry in time, leads directly to the law of conservation of energy. The fact that they are the same in every direction, a symmetry of rotation, leads to the conservation of angular momentum. This isn't just a mathematical curiosity. It is a foundational pillar of modern physics. It means that the very stability of our universe, the fact that energy is neither created nor destroyed, and that planets maintain their orbits, is a direct consequence of deep, underlying symmetries. These symmetries were baked into the universe at its birth, and the echoes we detect are vibrations within this symmetrical framework. Another giant whose work provides a mathematical window into the earliest universe is Roger Penrose. His contributions to cosmology are vast, but his work on conformal cyclic cosmology, while speculative, offers a stunningly mathematical vision of reality. More concretely, his earlier work on spacetime singularities, done with Stephen Hawking, used powerful topological arguments to prove that the Big Bang must have arisen from a singularity, a point of infinite density where the known laws of physics break down. This wasn't proven by experiment, but by the inexorable logic of mathematics applied to Einstein's equations. Penrose also developed the use of spinors and twistor theory, novel mathematical objects that provide a different perspective on spacetime itself, potentially offering a clearer way to understand the quantum nature of gravity at the moment of the Big Bang. His career demonstrates how pure mathematical imagination can light the path toward understanding the cosmos' most extreme moments. When we look at the specific patterns we're searching for, like the B-mode polarization in the cosmic microwave background, we are hunting for a specific mathematical signature. Theorists didn't just guess that inflation would create a curling pattern. They derived it rigorously from the equations of general relativity applied to a rapidly expanding universe. They calculated the precise statistical distribution that the temperature variations in the CMB should follow if they were indeed magnified quantum fluctuations. When the Planck satellite data matched this predicted pattern with breathtaking accuracy, it wasn't just a visual fit. It was a mathematical confirmation. The universe was following a script written in the language of statistics and probability, a script that began with the quantum jitters of the inflationary era. This leads to perhaps the most awe-inspiring idea of all, that the silent Big Bang's echoes might be encoded not just in any mathematics, but in fundamental mathematical constants. The strength of the gravitational wave signal, for instance, is directly tied to the energy scale of inflation. Measuring that signal would therefore give us a number, a fundamental parameter that describes the intensity of the universe's birth. Other constants, like the fine structure constant that governs the strength of electromagnetic interactions, seem fine-tuned to allow for complexity and life. Could these numbers themselves be the ultimate echo, the immutable, mathematical fingerprints of the process that spawned our cosmos? Some theorists speculate that these constants might not be random, but could be the unique outcome of the specific way our universe cooled and settled from its initial state, its vibrational modes freezing into the fixed values we measure today. Ultimately, mathematics grants us a form of extrasensory perception. Our instruments, as advanced as they are, have limits. We cannot build a detector large enough to directly measure the longest gravitational waves, and we cannot see past the veil of the CMB into the first instant of time. But mathematics allows us to transcend those physical limits. By writing down equations that we believe describe the fundamental nature of reality, we can project our understanding backwards, using the logic of calculus and geometry to peer into the singularity itself. We can predict what our instruments should hear before we even build them. The search for cosmic echoes is therefore a dialogue. We listen with our technology, interpret with our mathematics, and then build better technology to test our mathematical predictions. This abstract tool, this language of the universe, is what allows us to hear the whispers of a silent beginning that occurred long before any ear existed to hear it, transforming inaudible vibrations into the story of our existence. This idea that the universe might be fundamentally vibrational, built upon unheard frequencies that dictate its very structure, forces us to confront some of the most profound philosophical questions we can ask. For centuries, the dominant Western world has been materialist, the belief that reality is composed of solid, tangible matter and nothing more. But if the bedrock of everything is not a particle but a vibration, a wave of probability, then this materialist perspective begins to look like an illusion, a convincing facade built atop a deeper, more dynamic foundation. We are left wondering if the universe is less like a gigantic clockwork mechanism of bumping billiard balls and more like a grand cosmic symphony, where what we perceive as solid objects are merely the peaks and troughs of intersecting waves, temporary harmonies in an endless flow of energy and information. This is not a new thought experiment. It echoes ideas that have fascinated philosophers for millennia. Over 2,000 years ago, Plato introduced his theory of forms, suggesting that the physical world we experience is just a shadowy projection of a higher, more perfect realm of ideal concepts. He even used the metaphor of music and harmony to describe the soul and the cosmos. In a striking parallel, the vibrational view of reality proposes that the tangible world of matter is a manifestation of underlying, unseen frequencies, a modern scientific take on an ancient philosophical intuition. The quantum field, with its specific vibrations giving rise to particles, could be seen as a kind of mathematical form, a perfect blueprint from which our imperfect reality is cast. The silent Big Bang, then, wasn't just a physical event. It was the moment the first note was struck, setting the fundamental tone for the entire symphony of existence. This leads us directly to the so-called hard problem of consciousness, articulated by modern philosopher David Chalmers. The problem is simple to state but seemingly impossible to solve. Why and how does physical processing in the brain give rise to subjective, inner experience? Why do we have a rich internal life of thoughts, feelings, and sensations? If reality is indeed a vibrational construct, it opens up a radical possibility. Perhaps consciousness is not merely a byproduct of complex neural computation, but is itself a fundamental property of the universe, akin to space and time. In this view, the brain might not be generating consciousness but rather receiving it, acting as a sophisticated transducer, like a radio tuning into and interpreting a field of vibrational information that permeates all of reality. The frequencies that shape galaxies might also be the medium through which consciousness interacts with the physical world, offering a potential bridge between the objective cosmos and our subjective experience of it. The founder of quantum theory, Max Planck, seemed to hint at this deep connection long before modern cosmology had even conceived of inflationary echoes. He famously stated, "I regard consciousness as fundamental. I regard matter as derivative from consciousness. We cannot get behind consciousness. Everything that we talk about, everything that we regard as existing, postulates consciousness." This is a staggering statement from one of the architects of modern physics. It suggests that mind is not an accidental guest in a mechanical universe, but is woven into its very fabric. If the primordial frequencies from the universe's birth are the foundational code, then consciousness might be the process that interprets that code, the means by which the universe becomes aware of itself. Our quest to detect these echoes then becomes more than a scientific endeavor. It becomes a journey of self-discovery, an attempt to listen to the faint vibrations that not only shaped the stars but may also underlie our own capacity to wonder about them. This perspective completely transforms how we see our place in the cosmos. We are no longer separate observers looking out at a static, external universe. Instead, we are participants in a dynamic, resonant entity that is still unfolding, still vibrating from its silent beginning. Every act of observation, every measurement made by our instruments, is an interaction with this vibrational field. The cosmos is not a frozen sculpture but a living, breathing process of becoming, and we are inextricably linked to that process through the very frequencies that constitute our being. This is a vision of reality that is both humbling and empowering, suggesting that the echoes of creation are not just out there in the depths of space, but are also resonating within the deepest structures of our minds, connecting the birth of the universe to the birth of thought itself in an unbroken chain of vibration. Long before the first interferometer was conceived or the equations of inflation were written, the human imagination was already tuned to the idea of a universe built on vibration. This profound intuition that reality is fundamentally resonant and harmonious echoes through the annals of history, connecting ancient mysticism to cutting-edge cosmology. The concept of a silent, vibrational beginning is not a modern invention but the rediscovery of a truth that has whispered to us for millennia, a thread of understanding woven through the tapestry of human thought. Perhaps the earliest and most elegant expression of this idea comes from the ancient Greek philosopher Pythagoras and his followers in the 6th century BCE. According to legend, Pythagoras was passing by a blacksmith shop when he noticed the different notes produced by hammers of various weights striking anvils. This simple observation led him to experiment with a monochord, a single-stringed instrument, where he discovered that dividing the string into simple ratios produced harmonious intervals, a half for the octave, 2/3 for the fifth, and so on. From this, he made a breathtaking leap of logic. If simple mathematical ratios create harmony in music, perhaps the entire cosmos is ordered by the same mathematical principles. He proposed that the planets, as they moved through the heavens, Each produced a unique tone based on their orbital speed and distance, together creating a music of the spheres, a celestial symphony too perfect and too vast for mortal ears to hear. This was not a literal sound but a metaphysical harmony, a vibrational order underlying all of creation, and it established a powerful link between mathematics, music, and the cosmos that would inspire scientists for centuries. This fascination with cosmic harmony did not fade with the ancients. It was powerfully revived during the scientific revolution by the brilliant astronomer Johannes Kepler. A devout Pythagorean, Kepler was utterly convinced that God had constructed the universe according to geometric and harmonic principles. As he struggled to make sense of the precise orbital date painstakingly recorded by his mentor, Tycho Brahe, he sought not just any mathematical description, but the correct one, the one that would reveal the divine musical score. In his work Harmonices Mundi, The Harmony of the World, published in 1619, he laid out his third law of planetary motion, which mathematically relates a planet's orbital period to its distance from the Sun. But for Kepler, this was more than just a physical law. It was a musical chord. He assigned each planet a note based on its minimum and maximum orbital speeds, creating a musical scale for the solar system. He even composed a short, haunting melody for the Earth, which he noted sings "My Far My" for misery and famine, perhaps a commentary on the hardships of human existence. While we now know space is a vacuum that cannot carry sound, Kepler's intuition was profoundly correct in a different way. The precise mathematical ratios he uncovered are a form of music, the silent music of gravitational forces and orbital resonances that keep the solar system in perfect dynamic balance. The concept of a medium that carried these vibrations also has deep historical roots, most notably in the idea of the ether or ether. From ancient Hindu scriptures describing Akasha as the primordial space that is the source of all sound and matter, to Aristotle's quintessence, the fifth element that permeated the celestial realm, the belief in an invisible, all-pervading substance was widespread. In the 19th century, this idea reached its scientific peak as physicists postulated the luminiferous ether as the necessary medium through which light waves traveled, much like sound waves travel through air. This belief drove experiments like the famous Michelson-Morley study in 1887, which famously failed to detect the ether's drag on Earth's motion. While this failure ultimately led Einstein to his theory of relativity and the dismissal of the ether as a physical substance, the concept never truly vanished. It simply transformed. Today, we speak of quantum fields, invisible, energetic entities that fill all of space and whose vibrations give rise to particles. The Higgs field, which grants other particles their mass, is a direct descendant of the ether concept, a modern scientific validation of the ancient intuition that space is not empty but alive with unseen, vibrational activity. This thread of thought extends right into the modern era with visionary inventors like Nikola Tesla, who was utterly obsessed with resonance and vibration. Tesla understood that everything has a natural frequency at which it most easily vibrates. He famously claimed that by finding the exact resonant frequency of a structure, he could use a small mechanical oscillator to build up vibrations until the structure shook itself apart. A legend says he once nearly brought down a building in New York City with such a device. But his grander vision was cosmic. He believed that the Earth itself had a specific electrical resonance and that by tapping into it, he could transmit unlimited electrical power wirelessly through the ground. He spent years trying to build a global system of towers to achieve this, a dream that ultimately went unfulfilled but which demonstrates the enduring power of the resonant worldview. Tesla was listening for the fundamental note of the planet itself, attempting to harmonize human technology with the hidden frequencies of the Earth. What is truly stunning is how these historical intuitions, once dismissed as mystical or philosophical speculation, are now finding startling echoes in our most advanced scientific theories. Pythagoras' belief that reality is mathematical is the unspoken assumption underlying all of theoretical physics. Kepler's orbital harmonies are today studied as gravitational resonances that stabilize solar systems. The ancient concept of the ether has been reincarnated as the quantum vacuum, a seething sea of energy not unlike Tesla's visions of an energized Earth. The silent Big Bang and its ensuing symphony of gravitational waves and quantum vibrations is the modern, empirical counterpart to the music of the spheres. This long, unbroken chain of thought reveals a deep and enduring human quest to understand the universe not as a chaotic accident, but as an ordered, harmonious, and vibrational whole. Our ancestors may not have had the mathematics or the technology to prove it, but they heard the whisper of a fundamental truth, that we are all living in a cosmic symphony, and we are only now beginning to learn how to listen. This fascinating intersection of science and story suggests that humanity's oldest narratives might contain intuitive truths about the cosmos, preserved not in equations but in metaphor. Consider the creation account in the Hebrew Bible. It does not begin with a thunderous explosion, but with a formless void, a deep and silent darkness. Then the first act of creation is not a sound but a command, a spoken word that emerges from the silence. Later, the prophet Elijah does not find the divine in the powerful wind, the earthquake, or the fire, but in a still, small voice, a gentle whisper that follows the cacophony. This profound theme of a quiet, subtle beginning stands in stark contrast to the popular, noisy imagery often associated with divine power, pointing instead toward a more fundamental, understated origin. This concept of a silent, void-like beginning is echoed powerfully in Eastern traditions. In Hindu philosophy, the ground of all being is often described as shunyata, a Sanskrit term that translates not to mere emptiness, but to a fertile void, a potentiality from which all things arise. The universe is said to emerge from this silent, unmanifest state, a concept deeply resonant with the scientific idea of the quantum vacuum, which is not truly empty but seethes with potential energy. Similarly, the Taoist principle of the Tao, famously described as eternal and nameless, is the uncarved block from which the 10,000 things, the entire manifest world, are born. It is the silent, underlying principle that precedes and generates all action and noise. These ancient ideas feel less like primitive superstition and more like profound philosophical intuitions about the nature of reality, arrived at through contemplation rather than calculation. The renowned mythologist Joseph Campbell spent his life studying these common threads across the world's cultures, what he called the monomyth. He argued that myths are not falsehoods to be discarded by science, but are instead metaphors clothed in the imagery of their time, designed to convey psychological and cosmological truths about the human condition and our place in the universe. The recurring theme of creation emerging from a silent, formless state is one of these universal motifs. Campbell might suggest that this motif endures because it points to a fundamental human understanding, a deep-seated recognition that order does not typically emerge from prior chaos with a bang, but often crystallizes quietly from a state of potential. These stories are humanity's first cosmology, our initial attempt to answer the biggest questions, and their persistence across millennia hints that they might be touching on something real, something that our most advanced physics is only now beginning to articulate with mathematics. The late astronomer Carl Sagan beautifully championed this very connection between cosmic wonder and human storytelling. He saw science not as an enemy of myth, but as a way to uncover the true poetry and grandeur embedded within those ancient narratives. In his seminal series, Cosmos, he stated, "The cosmos is also within us. We're made of star stuff. We are a way for the cosmos to know itself." This poetic idea reframes the scientific pursuit. When we point our telescopes and detectors at the heavens, searching for the faint whispers of the Big Bang, we are not just conducting a technical experiment. We are part of a timeless human journey to understand our origins. The stories of a still, small voice and a fertile void were early chapters in that journey. Our modern search for primordial gravitational waves and quantum fluctuations is simply the latest chapter, written in a different language but driven by the same fundamental awe. What is truly remarkable is how these cultural echoes mirror the physical echoes we now hunt for with our technology. The myths are the cultural echoes, the stories passed down through generations that preserve an intuitive sense of a silent beginning. The primordial gravitational waves are the physical echoes, the actual vibrations traveling through space for billions of years. One is a narrative passed through time, the other is a signal traveling through space. Both are faint, difficult to detect, and require careful interpretation to understand. Both point back to a moment of profound genesis. This parallel suggests a deep and perhaps unconscious human attunement to the fundamental nature of reality, a sense that the universe's birth was not a violent rupture but a subtle emergence, a transition from a state of silent potential into the vibrant, noisy, and manifest cosmos we inhabit today. Our oldest stories and our newest science are, in this light, singing the same song in different keys, both listening for the same ancient, silent truth. It's easy to view our search for these ancient cosmic whispers as a purely abstract pursuit, a magnificent but ultimately impractical quest to satisfy our curiosity about the distant past. Yet the relentless drive to detect the faintest vibrations in the fabric of reality has consistently produced a cascade of unexpected and transformative technologies that shape our modern world. The same principles that govern the resonance of gravitational waves and the quantum hum of the early universe are being harnessed in laboratories and hospitals, turning the poetry of cosmology into the prose of practical innovation that touches every aspect of our daily lives. Consider the device in your pocket, your smartphone. Its ability to tell you exactly where you are on the planet with astonishing accuracy is powered by the Global Positioning System, a network of satellites each containing an atomic clock of unimaginable precision. These clocks are the beating heart of GPS, and their accuracy is a direct descendant of our understanding of fundamental vibrational principles. They don't tell time by counting the swings of a pendulum. They measure the unwavering vibrational frequency of atoms, typically cesium or rubidium, as they transition between energy states. This frequency is nature's most perfect metronome, an atomic vibration so stable that it would lose less than a single second over millions of years. The theory that allows us to understand and manipulate these atomic vibrations is quantum mechanics, the very same framework that describes the quantum fluctuations that seeded all galaxies. Without this deep, fundamental research into the vibrational nature of reality, the entire concept of precise global navigation would simply collapse. Every time you use a ride-sharing app, get directions, or even time-stamp a financial transaction, you are relying on technology born from our quest to understand the universe's most basic rhythms. This connection extends far beyond navigation and into the realm of medicine, where vibrational principles are literally saving lives. The detailed images from an MRI machine, which allow doctors to peer inside the human body without a single incision, are created by listening to the resonant frequencies of atoms within our tissues. The process involves aligning the spin of hydrogen atoms using powerful magnets and then pinging them with a specific radio frequency. When the radio wave is turned off, the atoms release that energy, relaxing back to their original state and emitting a faint signal of their own. Each type of tissue, muscle, fat, tumor, blood relaxes at a slightly different rate and frequency. The MRI machine acts like a sophisticated cosmic ear, listening to this symphony of returning vibrations and translating them into a detailed anatomical map. The mathematical techniques used to process this complex signal, particularly Fourier analysis, are identical to those used by cosmologists to sift the faint signal of primordial gravitational waves from the overwhelming noise of the cosmos. The same digital archaeology that uncovers the secrets of the Big Bang also helps radiologists uncover hidden ailments, demonstrating a beautiful symmetry between the macrocosm and the microcosm. Perhaps the most exciting frontier where cosmic principles meet earthly application is in the development of quantum computing. These revolutionary machines aim to harness the bizarre laws of quantum physics to perform calculations that are utterly impossible for even the most powerful classical supercomputers. Instead of using bits that are either a 0 or a 1, quantum computers use quantum bits or qubits, which can exist in a state of superposition, being both 0 and 1 simultaneously. What defines the state of a qubit? Often, it is a vibrational property. In some of the most advanced systems, qubits are tiny circuits that resonate at microwave frequencies, or individual ions suspended in electromagnetic fields whose vibrational states are controlled with lasers. Maintaining the fragile coherence of these qubits, preventing their quantum vibrations from decohering into noise, is the central challenge of the field. This is not so different from the challenge faced by the LIGO team in isolating the clean, pure signal of a gravitational wave from terrestrial vibrations. The extreme isolation and cooling technologies developed for both pursuits are pushing the boundaries of material science and engineering. As innovators like Elon Musk have often highlighted, the pursuit of ambitious, fundamental goals, whether it's listening to the cosmos or building a quantum computer, inevitably forces the development of new tools and techniques that spill over into countless other industries, driving progress in ways that are impossible to predict at the outset. This relentless innovation, spurred by pure curiosity, ultimately builds a brighter future for everyone. The sensors developed to listen for the universe's faintest whispers are finding uses in monitoring the structural health of bridges and buildings, detecting the microscopic vibrations that precede a failure. The advanced materials created to shield experiments from the slightest tremor are leading to better soundproofing and insulation. Even our efforts to understand the vibrational nature of dark matter could one day unlock entirely new forms of energy production or propulsion. The silent Big Bang's echoes are more than just a historical artifact. They are a continuous source of inspiration, a catalyst that pushes human ingenuity to its absolute limits. The drive to understand the most fundamental aspects of reality consistently proves to be one of the most powerful engines of practical progress, transforming the abstract music of the cosmos into the tangible rhythm of human advancement. But with this profound new understanding of the cosmos comes an equally profound responsibility: the ability to listen to the very fabric of reality, to potentially harness the principles that underpin existence itself, is not just a scientific achievement, it is a form of power. And as the old adage reminds us, with great power comes great responsibility. The knowledge that unseen vibrational forces might shape everything from the largest galaxies to the smallest particles forces us to confront a critical question. Once we learn to truly listen to these cosmic whispers, how will we choose to use that ability? The history of science is unfortunately littered with breakthroughs that were first weaponized, from nuclear fission to synthetic biology. The same gravitational wave detectors that allow us to hear black holes collide could, in theory, be refined to detect subterranean structures with unimaginable precision, or worse, be developed into a new form of long-range sensing for warfare. The principles of resonance that might explain galaxy formation could also be explored for disruptive purposes, from engineering seismic events to manipulating the human nervous system with targeted frequencies. This isn't science fiction, it's a foreseeable ethical challenge on the horizon of advanced physics. These concerns place us squarely in the domain of philosophers like Nick Bostrom at the University of Oxford, who has spent decades studying the existential risks of emerging technologies. Bostrom's work forces us to look far beyond immediate applications and consider the long-term, civilization-level implications of gaining deep cosmic knowledge. He might argue that the ability to manipulate fundamental forces, even on a small scale, constitutes a critical threshold, a point where our technological maturity could potentially outpace our wisdom. The very tools we use to listen for the universe's creation story could be repurposed in ways that threaten its most beautiful product, conscious life. This isn't a call to halt research. It is a powerful argument for proactive and robust ethical frameworks developed in parallel with the science itself. We need a global conversation involving not just physicists and engineers, but ethicists, policymakers, and the public to establish clear guidelines before these capabilities are fully realized. The goal must be to ensure that this cosmic knowledge serves as a tool for unification and advancement, not for division and destruction. This responsibility extends beyond preventing obvious misuses. It also encompasses ensuring equitable access to the benefits of this knowledge. The technological spin-offs from fundamental physics research from the World Wide Web born at CERN to the medical imaging breakthroughs from MRI technology have a history of transforming society. As we develop even more sensitive sensors and powerful computers to decode cosmic echoes, we must be intentional about directing these innovations towards solving human problems. This means actively working to prevent a scenario where the fruits of understanding the universe become the exclusive property of a few powerful nations or corporations. The data from telescopes and gravitational wave observatories are increasingly made open to the international community, fostering a collaborative spirit. This model of open science must be protected and expanded, ensuring that insights into the nature of dark energy or primordial vibrations can lead to breakthroughs in clean energy, materials science, or communications technology that benefit all of humanity, not just a privileged few. Ultimately, the quest to understand the silent Big Bang is more than a technical challenge. It is a test of our species' collective character. It asks whether we can cultivate not just intelligence, but wisdom. Can we approach the universe's deepest secrets with a sense of humility and reverence, rather than sheer domination? The knowledge that we are all, at our core, vibrational beings connected to a cosmic symphony could foster a deeper sense of global citizenship and shared destiny. Or it could be twisted to serve narrower, more divisive interests. The choice is ours to make. The duty of the scientist, and indeed of all society, is to foster that wisdom with the same passion we pursue discovery, ensuring that as we learn to listen to the universe, we do so with empathy, foresight, and an unwavering commitment to the future we all share. So where do we go from here in this grand quest to listen to the universe's faintest murmurs? The current era of discovery, as groundbreaking as it is merely a prelude. We are now on the cusp of a monumental leap, a new age of cosmology powered by a suite of next-generation instruments so sensitive they promise to turn the whispers we've struggled to hear into a chorus of clear, undeniable cosmic revelation. This isn't just about building bigger versions of what we have. It's about a quantum jump in technology, collaboration, and ambition, designed to probe the very limits of what is knowable about our silent beginning. Leading this charge on the cosmic microwave background front is an incredible project known as CMB-S4, the Cosmic Microwave Background Stage 4. Think of this not as a single telescope, but as a coordinated army of them. The plan is to deploy an unprecedented array of over 21 telescopes at the South Pole and another in the high Chilean Andes, equipped with a staggering 500,000 detectors. This massive scale is necessary to achieve a sensitivity that is simply unimaginable with current technology. The primary goal is to finally, definitively, capture the elusive curling B-mode polarization in the CMB, the smoking gun of primordial gravitational waves from inflation. But CMB-S4 will do far more than just that. By mapping the CMB's polarization with such exquisite detail, it will also act as a powerful neutrino detector, weighing the lightest particles in the universe by how they subtly alter the background radiation's pattern. It will shed new light on dark energy by measuring the gravitational lensing of the CMB, mapping the distribution of all matter, both seen and unseen, across cosmic history. It is, in essence, a multi-purpose cosmic observatory that will use the oldest light in the universe as a backlight to illuminate every hidden corner of physics. While CMB-S4 scans the sky from the most extreme environments on Earth, a revolution is also brewing for gravitational wave astronomy. The current ground-based detectors like LIGO and Virgo have opened a new window, but they are limited to hearing the high-frequency chirps and rumbles of stellar mass black holes and neutron stars. To listen to the lower frequencies, like the steady hum of supermassive black hole binaries or the primordial rumble from the Big Bang, we must go to space. The Laser Interferometer Space Antenna, or LISA, is that dream made real. This ambitious mission, led by the European Space Agency with NASA collaboration, will consist of 3 spacecraft flying in a perfect triangular formation, trailing behind Earth in its orbit around the Sun. Each side of this triangle will be 2.5 million kilometers long, creating a laser interferometer of staggering scale. In the pristine quiet of space, free from Earth's seismic rumble, LISA will open the low-frequency gravitational wave window for the first time, listening to the symphony of the cosmos in a register we have been completely deaf to until now. But even that is not the end of the roadmap on the ground. Looking further ahead, the Einstein telescope represents the future of terrestrial gravitational wave science. Envisioned as a subterranean observatory with arms 10 kilometers long, over 3 times longer than LIGO, and arranged in a triangular shape for better source localization, this facility will be built deep underground to isolate it from seismic noise. Its sensitivity is designed to be at least an order of magnitude greater than our current detectors. Cosmologist Risa Wechsler has expressed immense excitement for what this could mean, noting that with such precision, we could detect every black hole merger in the observable universe, effectively taking a cosmic census of these enigmatic objects. The Einstein telescope would allow us to test general relativity to its absolute limits and potentially hear the faint gravitational wave background from the early universe, a constant hum that would be the combined echo of countless inflationary events. Beyond these colossal projects, the hunt is also on to directly identify the Chinese letter of dark matter. While not searching for waves in the traditional sense, experiments like LUX Zeppelin and the upcoming Darwin project are using ultra-pure liquid xenon in tanks buried deep underground to listen for the infinitesimal ping of a dark matter particle bumping into a xenon nucleus. Other innovative approaches, like the Action Dark Matter experiment, are essentially giant, high-tech radio receivers trying to tune into the specific frequency that would be emitted if actions, a leading dark matter candidate, were to decay in a magnetic field. Finding this frequency would not only solve the dark matter mystery, but would also provide a direct link to the types of light particles that could have been copiously produced during the inflationary period, once again connecting the dots back to the universe's first moments. The timeline for these revelations is measured not in years but in determined decades of work. LISA is currently slated for launch in the mid-2030s. The Einstein Telescope and CMB-S4 aim to be operational in the 2030s as well. The data they collect will take further years to analyze and interpret. This is a long game, a testament to human patience and perseverance. The researchers designing these projects today may not be the ones who make the ultimate discovery. They are planting trees whose shade they know they may never sit under. Yet they pursue it with unwavering passion because the potential prize is nothing less than a new origin story for our cosmos. The next era of exploration promises to be the most transformative yet, moving us from the first tentative listening to a full and rich understanding of the cosmic symphony that has been playing since the very first silent note. Yet the most profound and controversial frontier of this interdisciplinary exploration lies in the realm of consciousness itself. Could the very phenomenon of subjective experience, our thoughts, feelings, and awareness, be connected to these foundational cosmic vibrations? This is not a new idea, but it is one that is being re-examined through a modern lens. The Oxford mathematician and physicist Sir Roger Penrose, for instance, has long argued that the human brain's ability to grasp non-computable truths suggests its workings cannot be explained by classical physics alone. Together with anesthesiologist Stuart Hameroff, he proposed the orchestrated objective reduction theory, or ORCH. This highly speculative but fascinating model suggests that consciousness arises from quantum vibrations happening within structures inside our brain's neurons called microtubules. These tiny protein-based tubes are thought to act as quantum processors, and Hameroff proposes that their vibrations could be influenced by deeper-level spacetime geometry, potentially even by the fundamental ripples from the universe's birth. In this view, our conscious moment-to-moment experience might be a resonant process, a symphony of quantum vibrations playing out inside our heads that could, in theory, be tuning into a broader cosmic frequency. Naturally, such ideas venture far from the mainstream and are met with significant skepticism from the broader scientific community. Critics point out that the warm, wet, and noisy environment of the brain is likely far too chaotic to support the delicate quantum coherence such theories require. Figures like Rupert Sheldrake, who proposes the concept of morphic resonance, a controversial idea suggesting that natural systems, including minds, inherit a collective memory from all previous things of their kind, are often placed firmly on the fringe. While these concepts capture the public imagination, they lack the rigorous experimental evidence required for widespread scientific acceptance. It is crucial to navigate this territory with a clear distinction between established science and speculative hypothesis, appreciating the creative thinking while acknowledging the current absence of concrete proof. The value of these more controversial thinkers often lies not in providing answers, but in asking provocative questions that challenge the boundaries of our current paradigms and force us to consider possibilities we might otherwise dismiss. This push towards a more holistic understanding is perhaps the most valuable outcome of this entire interdisciplinary pursuit. For too long, academic fields have operated in isolated silos, with physicists, biologists, and philosophers rarely engaging in deep conversation. The concept of the silent Big Bang and its enduring echoes provides a powerful narrative that can bridge these divides. It suggests a universe that is not a collection of separate domains but a deeply interconnected, vibrational whole. The same fundamental principles that govern the formation of galaxies might also be subtly guiding the folding of a protein or the firing of a neuron. This doesn't require a mystical leap. It simply invites a broader perspective, one where experts from vastly different fields collaborate to look for common patterns and shared languages, much like musicians from different genres coming together to find a new harmony. Ultimately, this line of inquiry brings our cosmic story full circle in a deeply personal way. It proposes that the echoes of the silent Big Bang are not just out there in the depths of space, but are also right here, resonating within the very fabric of life and mind. The carbon atoms in our cells were forged in the hearts of stars that formed from those primordial density fluctuations. The water that flows through our bodies carries a molecular structure that responds to energy and vibration. It is not a huge logical leap to wonder if the processes that govern life and consciousness might also be attuned, in some subtle way, to the universe's fundamental frequencies. This perspective transforms our quest from a purely external investigation of the cosmos into an intimate exploration of our own place within it, suggesting that by listening to the deepest echoes of the universe, we might ultimately be listening to the faint, vibrational whispers of our own existence. Yet for every thrilling announcement and every elegant theory, there is an essential counterbalance, a chorus of skepticism and rigorous debate that ensures science remains a process of discovery, not declaration. The path to understanding the universe's deepest secrets is not a straight line paved with unanimous agreement, but a winding road filled with wrong turns, heated arguments, and necessary corrections. This healthy friction is not a sign of weakness in cosmology. It is the very engine that drives it forward, forcing ideas to prove their worth against the unforgiving standards of evidence and logic. Perhaps no modern event illustrates this self-correcting mechanism better than the Bicep 2 incident. The year was 2014, and the atmosphere was electric. A team of researchers using a specialized telescope at the South Pole announced they had detected the holy grail of cosmology, the distinct curling pattern in the cosmic microwave background known as B-mode polarization. This signal was interpreted as the direct imprint of primordial gravitational waves, the long-sought proof of cosmic inflation. Headlines around the world proclaimed a monumental breakthrough, and for a brief, exhilarating moment, it seemed we had finally heard the echo of the Big Bang itself. But the celebration was short-lived. Other scientists, particularly those working with the European Space Agency's Planck satellite, immediately raised a red flag. They pointed to a formidable confounding factor, polarized dust within our own Milky Way galaxy. This interstellar dust, when aligned by magnetic fields, can produce a polarized signal that looks almost identical to the primordial one Bicep 2 claimed to have found. The ensuing collaboration between the teams to cross-check the data was a masterclass in scientific integrity. The final, joint analysis revealed the painful truth: the signal could be entirely explained by galactic dust. There was no need to invoke inflation. It was a spectacular false alarm, a sobering reminder that in the hunt for incredibly faint signals, extraordinary claims require extraordinary evidence, and the most exciting result is often the one that requires the most scrutiny. This kind of rigorous skepticism is applied not just to specific findings, but to entire theoretical frameworks. Take string theory, for instance. For decades, it has been one of the most prominent and mathematically beautiful candidates for a theory of everything. promising to unify gravity with quantum mechanics. Yet it has also attracted some of the most pointed criticism from prominent physicists. Peter Woit, a theoretical physicist at Columbia University, articulates a central frustration in his book, Not Even Wrong. The title comes from a phrase attributed to Wolfgang Pauli, implying a theory is so ill-defined that it cannot even be tested to be proven false. Woit and others argue that string theory, for all its mathematical elegance, has yet to make a single unique, testable prediction that could confirm or refute it. After over 40 years of development, it remains a dazzling piece of abstract mathematics without a clear connection to experimental reality. Similarly, Lee Smolin, a physicist at the Perimeter Institute, critiques what he sees as the field's lack of progress on its core promises and its tendency to proliferate into a nearly infinite landscape of possible universes, which he argues makes the theory ultimately untestable and therefore, in a scientific sense, vacuous. These are not dismissive attacks but serious challenges from within the community, pushing for a clearer link between theoretical elegance and empirical proof. Beyond these grand theories, healthy debate also surrounds the very interpretation of the data we do have. The cosmic microwave background is our most valuable snapshot of the infant universe, but reading it is like interpreting a complex ancient text. Different scholars can see different patterns. Some researchers propose that certain large-scale anomalies in the CMB, like the mysterious cold spot, could be evidence of something more exotic than standard inflation, perhaps even a collision with another universe in the multiverse. The majority of cosmologists, however, argue that these features are likely just statistical flukes, cosmic pareidolia where we see meaningful patterns in random noise. The standard model of cosmology, which includes dark matter, dark energy, and inflation, is incredibly successful at explaining a vast array of data, but it is not without its own conceptual puzzles. The hunt for alternatives is alive and well. Some theorists explore ideas like modified Newtonian dynamics as a replacement for dark matter, though these struggle to explain all the observations. Others work on bouncing cosmology models, where the Big Bang was not a true beginning but a transition from a previous contracting phase, offering a different origin story that completely avoids a singularity. These alternatives are vital as they prevent the mainstream view from becoming stagnant dogma and ensure that the simplest explanation isn't accepted just because it's the one we're used to. This entire process of challenge and debate is not a bug in the scientific system. It is its most vital feature. It is the reason we can have confidence in well-tested ideas like the Big Bang or plate tectonics, because they have survived decades of relentless attempted demolition from skeptical peers. The path to understanding cosmic echoes is not paved with confident certainty, but with meticulous questioning. Every proposed detection is met with demands for more data. Every elegant theory is challenged to make a falsifiable prediction. This might seem like a slow and frustrating way to build knowledge, but it is the only method we have for peeling away our own biases and wishful thinking to get closer to the truth. The debates over Bicep 2, string theory, and the nature of dark matter are not signs of a field in crisis. They are the sound of a field that is vibrantly alive, where the ultimate authority is not a person or an institution, but nature itself, revealed through experiment, observation, and an unwavering commitment to questioning everything. But how do we translate these incredibly complex, often abstract ideas from the realm of theoretical physics and advanced mathematics into something that captivates the imagination of someone without a science degree? The quest to understand the universe's silent beginnings isn't just for those wearing lab coats. It's a fundamental human story, and sharing that story with everyone is not just beneficial, it's essential. Public engagement transforms cosmology from an isolated academic pursuit into a shared cultural adventure, fostering a sense of wonder that can inspire the next generation of scientists and ensure continued support for the basic research that drives all discovery. The most successful outreach doesn't talk down to its audience. It invites them in, using creativity and relatable storytelling to turn everyone into a participant in the greatest detective story ever told. One of the most powerful tools for this has been the modern scientific documentary. Productions like the rebooted Cosmos series, hosted by the charismatic astrophysicist Neil deGrasse Tyson, have mastered the art of visual metaphor. They take an idea as mind-bending as the expansion of spacetime and illustrate it by having Tyson stand on a beautiful, animated beach with galaxies receding on the surface of an expanding balloon. This isn't dumbing down the science, it's smartening up the presentation, providing a crucial conceptual hook that allows a viewer to grasp the framework of an idea before delving into its complexities. Planetarium shows take this a step further into immersion. In the domed darkness, audiences don't just learn about the cosmic microwave background. They fly through it, seeing the subtle temperature variations that seeded all galaxies rendered in vivid color and 3 dimensions, transforming a map of data into a tangible landscape from the dawn of time. These experiences tap into a primal sense of awe, connecting people to the scale and beauty of the cosmos in a way a textbook simply cannot. The digital age has democratized this outreach even further, bringing the cosmos directly into our pockets. Social media platforms are now filled with scientists and educators who have become skilled communicators. They use short-form video to explain gravitational waves with the help of a stretched rubber sheet and some marbles, or employ engaging animations on YouTube channels like PBS Space-Time to unpack the intricacies of quantum fluctuations. A physicist can now live tweet from a major conference, giving thousands of followers a front-row seat to a groundbreaking announcement about the latest analysis from the James Webb Space Telescope. This direct access breaks down the traditional barriers between the researcher and the public, making science feel less like a remote institution and more like a collaborative, ongoing conversation. It allows for immediate answers to curious questions and humanizes the people behind the discoveries, showing the excitement, collaboration, and occasional frustration that are all part of the scientific process. This cultural shift towards greater accessibility is also reflected in the world of art and music. Composers create symphonies inspired by the data from gravitational wave detections, translating the chirp of colliding black holes into an auditory experience that is both scientifically accurate and emotionally moving. Visual artists collaborate with researchers to create installations that represent the unseen dark matter halos surrounding galaxies, giving form to the invisible forces that shape our universe. These collaborations are more than just pretty interpretations. They are a different mode of understanding. They allow people to connect with these concepts on an emotional and intuitive level, creating a lasting impression that complements the intellectual understanding gained from articles and lectures. When a person feels the awe of the universe, they are more likely to care about preserving our ability to continue exploring it. Ultimately, this widespread engagement creates a virtuous cycle. A public that is excited about fundamental science is a public that values it, advocating for government funding for agencies like NASA and the National Science Foundation, which are the lifeblood of these large-scale projects. It encourages private philanthropy aimed at supporting basic research, and perhaps most importantly, it inspires young students to see themselves as future scientists. A child who watches a documentary about the search for cosmic echoes might be inspired to pay more attention in math class, seeing it not as abstract homework but as the essential language for decoding the universe. That child could be the one who, in a few decades, devises the experiment that finally isolates the primordial gravitational wave signal from the background noise, completing a story that began with their own moment of childhood wonder. Ensuring that this cosmic conversation includes everyone isn't just about sharing answers, it's about empowering the next wave of questions. But as we pull back from the telescopes and the equations and the grand theories, we arrive at a moment that is perhaps the most profound of all. This isn't just about understanding the universe out there, it's about understanding what it means for us right here, right now. To truly absorb the idea that the very fabric of our being is woven from threads spun in the first silent moments of time is to undergo a quiet revolution in perspective. It invites a deeply personal introspection, a shift from seeing ourselves as separate observers of the cosmos to recognizing that we are active, vibrational participants within it. Consider the sheer chain of events that had to unfold with impeccable precision for you to be here, reading these words. The quantum fluctuations imprinted on the cosmos during inflation dictated where the first galaxies would form. Within one of those galaxies, a particular star, our Sun, coalesced in a region rich with the heavy elements forged in the heart of a previous generation of stars that lived and died. On the third planet orbiting that star, those same elements combined in a cosmic alchemy over billions of years, eventually forming a molecule capable of not just replicating itself, but of contemplating its own existence. You are not just a resident of the universe, you are the universe become conscious, a localized knot of space-time that has developed the capacity to feel, to think, and to wonder about its own origins. The carbon in your cells, the iron in your blood, the calcium in your bones, all of it is literal stardust, assembled according to a blueprint written in the faintest of whispers from the dawn of everything. This isn't a poetic metaphor, it's the bedrock of our astrophysical understanding. You are a walking, talking testament to a 14-billion-year-old story that began in silence. This realization naturally leads to a question of legacy. If the universe leaves echoes, what echoes do we leave behind? Our lives, though fleeting on a cosmic timescale, are not without their own vibrational impact. Every action we take, every word we speak, every connection we forge sends out ripples into the world around us, much like a pebble dropped in a pond. The kindness you show a stranger, the idea you share with a friend, the art you create, these are the frequencies you broadcast into the human network. They might seem small and insignificant against the backdrop of the cosmos, but so did those initial quantum fluctuations. They were unimaginably tiny, yet they grew to shape the entire cosmic web. In the same way, the small, positive vibrations we put out into the world can compound and amplify in ways we can scarcely imagine, influencing others and cascading through time long after we are gone. We may not generate gravitational waves, but we generate waves of consequence, and we have a choice in what kind of frequencies we choose to emit. This perspective cultivates a powerful sense of interconnectedness. The same fundamental forces that guide the dance of galaxies also govern the orbit of the Moon around our planet, which in turn pulls the tides that shape the environment where life first emerged. The same physics that describes the resonant vibrations of a string in a theory of everything also describes the resonant vibrations of the molecules that make up the air, allowing sound to travel to our ears. We are not just connected to the cosmos by our atomic Chinese letter. We are enmeshed in its ongoing physical processes, living within a continuous, dynamic flow of energy and information. Recognizing this can dissolve feelings of isolation and replace them with a profound sense of belonging to something vast, beautiful, and ancient. You are not a lonely spectator adrift on a tiny rock. You are an integral part of a magnificent, unfolding cosmic process. So how does this change your view of reality? It invites a shift from a mindset of scarcity to one of abundance. We often operate from a place of fear, seeing the world as a collection of separate entities competing for limited resources. But the cosmological view suggests a universe of immense, even infinite potential, born from a silent, generative act. It encourages us to see the world not as a static collection of things, but as a dynamic web of relationships and vibrations. The phone in your hand, the tree outside your window, and the person you love are all, at their most fundamental level, manifestations of the same underlying energetic fields, vibrating in different patterns. This isn't just a spiritual idea. It's what quantum field theory tells us about the nature of particles and forces. Seeing the world this way can foster a deeper sense of compassion, patience, and wonder in our daily interactions, because you begin to recognize the universe itself in everyone and everything you encounter. Ultimately, the silent Big Bang's most enduring echo might not be a gravitational wave or a temperature variation in the CMB. Its most profound echo might be consciousness itself, the universe's ability to reflect upon itself through us. Our curiosity, our drive to explore, our insatiable need to understand where we came from, these are not quirks of human nature. They are the cosmos waking up. They are the universe, after billions of years of evolution, finally developing the ears to hear its own origin story and the voice to tell it. So the next time you feel overwhelmed by the pace of daily life, take a moment to look up at the night sky. Remember that you are made of the echoes of a silent beginning, and that your very existence is part of the universe's continuous, resonant song. Your life is not a separate note. It is a unique and vital part of the everlasting harmony. This profound connection between the cosmos and human creativity is where art picks up the thread, translating the silent majesty of the universe into forms that speak directly to our emotions. When the mathematics becomes too abstract and the data too faint, artists step in to give form to the formless, giving us a visceral, emotional encounter with concepts that might otherwise feel distant and cold. They don't just illustrate the science, they interpret it, using their medium to ask a different kind of question, not how the universe works, but what it feels like to be a part of it. This is the power of artistic interpretation. It allows us to experience the wonder of cosmic silence with our entire being, not just our intellect. One of the most powerful examples of this is the work of composer John Luther Adams. His Pulitzer Prize-winning orchestral work, Become Ocean, is a stunning auditory representation of vast, powerful, and ancient forces. While not specifically about the Big Bang, the piece immerses the listener in a slowly unfolding, tidal soundscape that feels primordial and immense. The music swells and recedes in complex, overlapping waves, creating a sense of deep time and natural power that is utterly transporting. Listening to it, you can almost feel the gravitational pull of the moon, the slow drift of continents, or the silent, relentless expansion of spacetime itself. Adams creates what he calls a sonic geography, a place you can go to in your mind to viscerally comprehend the scale and rhythm of natural systems that are too large to see. His work doesn't describe the universe's birth. It makes you feel as though you are floating within its aftermath, a tiny witness to a beautiful, indifferent, and eternal process. In the visual arts, the challenge of representing the silent Big Bang has led to breathtaking collaborations that fuse data with design. Consider the work of artists who have taken the actual data from the Planck satellite's map of the cosmic microwave background, the faint, speckled pattern of hot and cold spots that is the universe's baby picture, and transformed it into large-scale installations. They might represent each temperature fluctuation with a subtly different shade of color or a physical pixel of varying height, creating a textured, topographical map of the infant cosmos that you can almost walk through. These installations take the coldest, most clinical data and render it as a tangible, almost sacred object. They allow us to stand in the presence of the oldest light in existence, not as a graph on a screen, but as a vast, immersive artwork that surrounds us. It's a powerful reminder that this blueprint for all structure isn't just a set of numbers. It's a physical reality, a fossilized echo that we can now perceive with our senses. Sound artists take this a step further by attempting to make the inaudible audible. They engage in a process called sonification, where they assign musical notes to scientific data. The most famous example of this might be the sonification of the first gravitational wave detection, where the chirp of two black holes merging was sped up into the range of human hearing, allowing us to literally hear space-time ring. But artists expand on this, creating compositions from the magnetic fields of planets, the radio emissions of distant pulsars, or the vibrational frequencies of theoretical strings. They are, in a very real sense, tuning into the universe's hidden symphony and playing it back for us. These pieces are more than just novelty. They are a genuine attempt to explore the universe through a different sense, offering a unique kind of understanding that complements the analytical work of scientists. It's a collaboration where the artist provides the ears and the scientist provides the score. This synergy between the laboratory and the studio is a two-way street that enriches both fields. Scientists often report that seeing their data interpreted through art gives them a new perspective on their own work, revealing patterns or evoking questions they hadn't considered before. The artist's freedom to explore metaphor and emotion can open up new avenues of scientific curiosity. Conversely, artists gain access to the most profound and cutting-edge narratives about reality, providing an endless wellspring of inspiration that is both intellectually rigorous and deeply meaningful. This partnership moves beyond simple outreach. It becomes a genuine dialogue between different ways of knowing, proving that the quest to understand our place in the cosmos is a fundamentally human endeavor that requires both the precision of logic and the depth of feeling. Together, they ensure that the story of the silent Big Bang is not just understood, but felt and remembered, echoing through our culture as more than just a theory, but as a part of our shared human experience. And this grand endeavor, this search for the faintest whispers of creation, is not a solo mission. It is perhaps the most ambitious and coordinated team effort in human history, a testament to what we can achieve when we look past the lines on a map and see ourselves as citizens of a single planet, united by a shared curiosity. Detecting the universe's most subtle signals requires a global network of minds and machinery, a collaborative spirit that transcends politics, culture, and language. This isn't just science, it's a powerful demonstration of our ability to work together for a goal that benefits all of humanity. Consider the monumental achievement of the Event Horizon Telescope, the project that gifted us the very first image of a black hole's shadow. That now iconic image of the fiery ring around the supermassive black hole at the heart of the Messier 87 galaxy was not the product of a single, massive dish. It was a symphony of synchronization. The EHT is a virtual telescope the size of the Earth itself, created by linking 8 radio observatories across the globe, from the high deserts of Arizona and the volcanic peaks of Hawaii to the frigid expanse of the South Pole and the mountains of Spain and Chile. To function as one cohesive instrument, every single one of these facilities had to record data from the same point in the sky at the exact same time, using atomic clocks so precise that their ticking is governed by the fundamental vibrations of atoms. The data collected was so vast it couldn't be sent over the internet. It was physically shipped on hundreds of hard drives to central processing centers in the United States and Germany, where supercomputers combined the signals. This required an unprecedented level of international coordination, trust, and shared purpose. Researchers from over 20 countries and 60 institutions worked for years to calibrate, analyze, and finally reveal the image that captivated the world. It was a moment that belonged to no single nation, but to everyone. This model of open collaboration is the lifeblood of modern cosmology. The Laser Interferometer Gravitational Wave Observatory itself, while based in the United States, is fundamentally an international project. Its discoveries are made by a collaboration of over 1,000 scientists from more than 100 institutions across more than 20 countries. When the first gravitational wave signal was detected, the team didn't just celebrate in Washington and Louisiana. There were celebrations in Germany, the United Kingdom, Italy, India, Japan, and Australia. The data from these detectors is shared freely among the collaboration, and the resulting scientific papers often have so many authors that the list can run for dozens of pages. This isn't about fame or individual credit, it's about the collective acceleration of knowledge. By pooling resources, expertise, and data, we achieve far more than any single country could alone. A physicist in India can work on the same data set as a graduate student in Brazil, each bringing their unique perspective to the analysis, refining the models, and pushing the understanding further. This commitment to openness extends beyond the core research teams to the entire world through the principle of open data. After a proprietary period where the initial discovery teams can verify their findings, vast troves of cosmic data are routinely released to the public. The information from space telescopes like Hubble, Kepler, and now the James Webb Space Telescope is made available to any astronomer or curious citizen with an internet connection. This democratizes discovery, allowing a brilliant researcher at a small university without a multi-billion-dollar budget to make a groundbreaking find using the same data as a scientist at NASA or the European Space Agency. It invites amateur astronomers and coding enthusiasts to sift through the information, sometimes leading to unexpected and delightful discoveries. This transparency builds trust and ensures that the fruits of this cosmic exploration belong to all of humankind, not locked away in private labs. This collaborative spirit does more than just advance science. It builds bridges between cultures and fosters a rare and precious sense of global community. Scientists working on these projects must learn to communicate across language barriers and cultural differences, finding a common tongue in the universal language of mathematics and physics. They share long nights at remote observatories in Chile's Atacama Desert, endure the harsh winter darkness together at the South Pole, and celebrate each other's successes with genuine camaraderie. NASA astrophysicist Michelle Thaler often speaks beautifully about this aspect of her work, noting that science is one of the most powerful tools for peace that we have. When you're working side by side with someone from a nation your own might have political tensions with, all focused on solving a puzzle that is bigger than all of us, those earthly divisions start to feel incredibly small and insignificant. You're not an American or a Russian or a Chinese scientist. You are a human being trying to read the story of the universe. This shared quest for understanding becomes a powerful antidote to parochialism, reminding us that beneath all our surface differences, we are all made of the same stardust, looking up at the same sky and wondering about the same silent beginnings. In a world often fractured by conflict, the global search for cosmic echoes stands as a shining example of what we can accomplish when we choose to look up and work together instead of looking down and pulling apart. While the theory of cosmic inflation has become the dominant framework for understanding our universe's first moments, Its very success has inspired physicists to ask a deeper, more provocative question: is it the only possible story? The pursuit of knowledge thrives on healthy skepticism and the exploration of alternatives, and cosmology is no exception. Beyond the well-trodden path of inflation lies a fascinating landscape of other ideas, some elegant, some bizarre, all offering radically different visions of how everything began. These are not mere footnotes, they are serious scientific proposals that challenge the mainstream view and force us to keep an open mind until the evidence speaks with one unambiguous voice. One of the most compelling alternatives is the concept of a bouncing cosmology. Imagine the universe not as a one-time creation event, but as part of an endless cycle of death and rebirth. In this view, our expanding universe was preceded by a previous phase of contraction, a big crunch, where all matter and energy collapsed back in on itself. But instead of ending in a definitive singularity, the universe reached a point of maximum density and then bounced. The repulsive force of quantum gravity, acting at these incredible extremes, would have reversed the collapse into the expansion we see today. This means the Big Bang was not the absolute beginning, but simply the latest turning point in an eternal cosmic cycle. Proponents of this model, which emerges naturally from theories like loop quantum gravity, suggest that each bounce would effectively reset the universe, but might not erase all information from the previous one. The faintest echoes from the pre-bounce universe could, in theory, have survived, imprinted as anomalous patterns in the cosmic microwave background, ghostly whispers from a cosmos that existed before our own. Another radical departure from the standard model is the idea of emergent spacetime. What if space and time are not the fundamental stage upon which the universe plays out, but are themselves secondary properties that condense from a more basic, non-spatial reality? Think of it like this: water is wet and fluid, but if you cool it down enough, its molecules will arrange themselves into the rigid, crystalline structure of ice. The properties of ice emerge from the collective behavior of the water molecules. Similarly, theories of emergent spacetime propose that what we experience as the four-dimensional fabric of the cosmos might actually be a kind of illusion, emerging from a vast network of entangled quantum information or from a reality built on discrete, tiny building blocks. In such a model, the Big Bang wouldn't be the beginning of everything, but rather the moment when spacetime as we know it first crystallized into existence. The physicist Carlo Rovelli, a leading figure in loop quantum gravity, often uses this kind of relational framework, suggesting that time itself might not be fundamental. In this view, the primordial echoes we seek might not be vibrations in spacetime, but rather the residual noise from the process of spacetime's very formation, a kind of cosmic static left over from its transition into being. Then there is string gas cosmology, an idea that springs from the same theoretical roots as string theory, but leads to a very different origin story. In this model, the early universe was a hot, dense, and chaotic gas of the fundamental strings that string theory posits as the building blocks of everything. This gas was confined to a small, nine-dimensional space. As the universe evolved, only 3 of those spatial dimensions underwent expansion, growing to the vast cosmos we see, while the other 6 dimensions remained curled up into the tiny shapes that determine the laws of physics within our realm. This model can also explain the uniformity and flatness of the universe without a period of rapid inflation, instead relying on the thermodynamic behavior of the string gas to naturally smooth everything out. The primordial fluctuations that seeded galaxies would have a different, though sometimes similar, statistical signature than those predicted by inflation, providing a potential way for future experiments to distinguish between the two. The true test of any scientific theory, however, is how its predictions stack up against cold, hard data. This is where these alternative ideas face their greatest challenge. The standard inflationary model made a very specific prediction about the pattern of temperature variations in the cosmic microwave background, a nearly scale invariant spectrum of fluctuations. When the Planck satellite mapped the CMB with exquisite precision, that prediction was confirmed with stunning accuracy. This was a huge win for inflation. Many alternative theories struggle to reproduce this exact pattern as naturally or as elegantly. Furthermore, the inflationary model provides a clear mechanism for generating the primordial gravitational waves that experiments are desperately searching for. While some bouncing cosmologies can also produce such waves, their predicted signal strength often differs. A definitive detection by a future observatory like the Simons Observatory or LIGO could therefore rule a whole class of alternatives in or out. For now, the lack of any confirmed anomalies in the CMB that would clearly point to a pre-Big Bang universe keeps these ideas on the fascinating but speculative fringe. This vibrant debate is not a sign of weakness in cosmology. It is its greatest strength. The existence of compelling alternatives ensures that inflation does not become a dogma. It forces its proponents to sharpen their arguments, refine their predictions, and seek even more conclusive evidence. Experts like Neil Turok have long championed cyclic models, not out of contrarianism, but out of a desire to find a more elegant and complete theory that avoids the conceptual knot of a true beginning. Similarly, the work on emergent spacetime pushes us to think more deeply about the very nature of reality itself. By rigorously exploring these other paths, we are not abandoning the quest for truth. We are expanding it, ensuring that when we finally do hear the universe's first whisper clearly, we will have the full vocabulary needed to understand what it is truly trying to tell us. The story of our origins is still being written, and until the final chapter is confirmed by observation, every plausible and beautiful idea deserves its moment in the cosmic spotlight. If this journey into the echoes of the silent Big Bang has sparked a deeper curiosity, you are certainly not alone. The incredible thing about this field is that the tools to explore it further are more accessible than ever before, waiting for anyone with an internet connection and a sense of wonder. For those ready to dive down the rabbit hole, a universe of educational resources is available, carefully crafted by brilliant minds to guide you from casual interest to genuine understanding, no matter your starting point. For a truly foundational experience, begin with the words of the pioneers themselves. Alan Guth's book, The Inflationary Universe, is more than just a historical account. It's a thrilling, intellectual memoir that puts you in the mind of a theorist having a world-changing idea. Guth writes with a clarity and humility that makes even the most complex concepts feel approachable, detailing the puzzles of the standard Big Bang model that led him to propose cosmic inflation. It's a masterclass in how science actually works, filled with wrong turns, sudden insights, and the collaborative spirit that drives discovery. To complement this, the first 3 minutes by Steven Weinberg offers a beautifully written, classic exploration of the universe's very early history, painting a vivid picture of that searingly hot first chapter after the bang. When you're ready to move from the page to the screen, the digital world is your classroom. The PBS Space-Time YouTube channel, hosted by Matt O'Dowd, is an unparalleled resource for those who want to truly grasp the mathematics and physics behind these ideas without sacrificing depth. O'Dowd's episodes on topics like B-mode polarization, the cosmological constant problem, and the nature of quantum fields are dense, challenging, and incredibly rewarding, often employing clear animations and graphics to unpack equations that might otherwise seem impenetrable. For a broader survey of cosmic mysteries, the podcast Star Talk, hosted by Neil deGrasse Tyson, blends authoritative science with playful humor and celebrity interviews, making it a perfect and entertaining companion for a commute or a walk. For those seeking a more structured academic path, the opportunities are vast. Leading universities around the world now offer free online courses that can take you from the basics to the bleeding edge. Platforms like edX and Coursera host incredible offerings such as MIT's Astronomy, Exploring Time and Space, or the University of Chicago's Understanding the Universe, an Introduction to Astronomy. These courses provide video lectures, problem sets, and discussion forums, allowing you to learn at your own pace and even earn a certificate for your efforts. If you're feeling particularly ambitious, you can often find full semester lectures from top-tier institutions posted on YouTube, giving you a front row seat to the same education offered to students at Harvard or Stanford. The journey doesn't stop with formal courses. Staying current requires following the conversation as it happens. Websites like phys.org and space.com offer excellent daily news coverage of breakthroughs in cosmology and astrophysics, written for a general audience. For a deeper dive into the latest research papers and conference findings, the online magazine Quantum Magazine is in a class of its own, publishing long-form, deeply reported articles that explain new discoveries with unparalleled narrative flair and scientific accuracy. Their pieces on dark energy, gravitational waves, and the mysteries of inflation are like reading the first draft of history, written as it unfolds. This lifelong pursuit of knowledge is what transforms passive watching into active participation. Each book read, each video watched, and each course completed empowers you to not just accept these amazing ideas, but to engage with them critically, to question them, and to form your own connections. The story of our cosmic origins is still being written, with new chapters added by researchers every single day. By arming yourself with these resources, you become part of that ongoing conversation, ensuring that your sense of wonder is continually fed by the most powerful fuel there is, understanding. One of the biggest hurdles in understanding the true nature of the cosmos is untangling the web of popular myths that have wrapped themselves around the Big Bang. For decades, the term itself has been a source of confusion, conjuring an image that is both spectacular and spectacularly wrong. We picture a titanic fireball erupting at a single location within a vast, pre-existing emptiness, hurling matter outward like shrapnel from a cosmic bomb. This is the most common misconception, and it's utterly misleading. The Big Bang was not an explosion in space. It was a rapid, everywhere at once expansion of space itself. To grasp this crucial difference, let's ditch the bomb analogy and try a better one. Imagine the universe is the surface of a balloon, and glued to that surface are tiny dots representing galaxies. Now, as you inflate the balloon, every single dot starts moving away from every other dot. No dot is the center of the expansion. The center is inside the balloon, a point not on the surface, in a higher dimension we cannot access. The space between the dots, the fabric of the balloon's surface, is what's stretching. This is exactly what happens in our universe. Galaxies aren't racing away from us through a stationary space. The space between us and them is literally expanding, carrying them along for the ride. This is why astronomers observe that the farther away a galaxy is, the faster it seems to be receding, not because it's moving faster, but because there's more expanding space between us to compound the effect. This directly leads to another pervasive myth, the idea of an edge to the universe. If everything is flying apart from a central point, it seems logical that there must be a leading edge, a frontier where the expanding matter meets the void. But this is another trick of our intuition, which is built for thinking in 3 dimensions. The balloon analogy helps again. Does the surface of the balloon have an edge? A boundary, no, it is a finite but unbounded surface. You could travel forever in one direction and never hit a wall. You'd just loop back to where you started. Our universe could very well be the same, finite in volume but without any edge or boundary. Even if the universe is infinite, the Big Bang wasn't an explosion that happened at one point in that infinity. It happened everywhere simultaneously. As physicist Sean Carroll often explains, there is no center and there is no edge. The Big Bang wasn't a location in space. It was a moment in time, a state of the entire universe when it was incredibly hot and dense. This naturally brings us to the most mind-bending question of all. What was before the Big Bang? The classic and frustrating answer from modern cosmology is that the question might not make sense. We often think of time as a universal constant that has always been there, a stage upon which events unfold. But Einstein's theories welded time and space together into a single fabric, space-time. The Big Bang wasn't just the beginning of all matter and energy. According to our best models, it was also the beginning of space-time itself. Asking what happened before the Big Bang is like asking what is north of the North Pole. The concept of before requires time to exist, and if time itself began at that singularity, there simply is no before in any meaningful sense we can comprehend. Of course, this is an active area of research, and theories like the bouncing cosmology or the multiverse do propose a before. But in the standard model, the initial singularity is the ultimate boundary of our physics, a point where our equations break down and our understanding ends. It's not that there was nothing, it's that the very words was and there lose their meaning when applied to a state where time and space did not yet exist. Clearing up these foundational misconceptions is absolutely critical. If we're going to have any hope of understanding the subtle echoes from the universe's birth, those primordial gravitational waves and quantum fluctuations, we first need to wipe the slate clean of these intuitive but incorrect pictures. We have to be willing to let go of what feels obvious and embrace the universe on its own strange terms, building our knowledge from a place of accurate, if bewildering, facts rather than comforting fiction. And so our journey through the echoes of time brings us to a profound realization. The cosmos is not a silent, static painting but a dynamic, resonant entity, still humming with the vibrations of its own birth. We began by reimagining the Big Bang not as a cataclysmic roar but as a silent, rapid unfurling of spacetime itself, a concept that forever changes our origin story. From there, we tuned into the hidden language of the universe, from gravitational waves rippling through the fabric of reality to the quantum whispers that seeded every galaxy, star, and planet. We explored how cutting-edge technology, from LIGO incredible precision to the future promise of space-based observatories like LISA, is transforming us from passive observers into active listeners of the cosmic symphony. We ventured into the mysteries of dark matter and dark energy, considered the tantalizing possibility of a multiverse, and even glimpsed how the same vibrational principles that shape the cosmos might resonate through biology and consciousness. This exploration has revealed a universe that is far more interconnected, mysterious, and alive with possibility than we ever could have imagined. These discoveries challenge the very foundations of how we see reality. They invite us to move beyond a materialistic view of the world as a collection of solid, separate objects, and to instead perceive it as a vast, interconnected web of energy and information, a cosmic dance of vibrations. The notion that faint frequencies from the universe's first moment could still be influencing the formation of galaxies, the stability of solar systems, and perhaps even the processes of life itself, forces a radical shift in perspective. It blurs the line between the cosmic and the personal, suggesting that the same fundamental forces that guide the dance of distant quasars are also at work in the world around us and within us. This isn't just abstract physics, it's a new way of understanding our place in the cosmos, not as separate observers but as integral participants in an ongoing 14-billion-year-old story. We are not just living in the universe, we are the universe becoming aware of itself. The quest to hear these whispers is far from over. It is accelerating, driven by a new generation of telescopes, detectors, and the brilliant, collaborative minds of scientists around the globe. Projects like CMB-S4 with its 500,000 detectors, the space-based LISA Observatory, and the subterranean Einstein telescope promise to listen deeper and more clearly than ever before. They may soon provide the definitive evidence we need to confirm inflation, identify the Chinese letter of dark matter, or even detect the unthinkable, an echo from another universe. This is not the end of a story, but the beginning of a new and even more exciting chapter. The answers to these age-old questions are within our reach, waiting for that moment when our instruments finally become sensitive enough to isolate the signal from the noise, transforming a theoretical whisper into a measurable fact that will rewrite our textbooks. This entire journey underscores a simple yet breathtaking truth. The universe is not just something to see, it is something to hear. For all of human history, we have explored the cosmos with our eyes, building ever larger telescopes to capture faint photons that have traveled across space and time. But now we are developing a new sense. We are learning to listen to the cosmos through the subtle stretching and squeezing of space-time itself, hearing the collisions of black holes and the rumble of the Big Bang's aftermath. This shift from observation to audition opens a completely new window on reality, allowing us to probe regions of space and epochs of time that were previously invisible and inaccessible. It reminds us that our senses are limited and that the true nature of reality often lies just beyond their reach, waiting for our curiosity and ingenuity to find a way to perceive it. As we conclude, remember that this story is still unfolding and you are a part of it. The drive to understand where we came from is one of the most profound and defining traits of our species. It connects the ancient stargazer who first pondered the silent heavens to the modern physicist analyzing data from a South Pole telescope. That shared sense of wonder is our greatest inheritance. So the next time you look up at the night sky, try to remember that you are not just looking out into space, you are also listening back into time. The silent echoes of creation are still traveling through the cosmos, and through us, the universe is finally developing the ears to hear its own origin story. Keep wondering, keep questioning, and never stop.